We have a little bit late, and our first speaker is about to join. He has some network issue. We are not able to connect him right now. So let's welcome our second speaker of the day, Dr. Somnath Acharya. He is an experimental condensed matter physicist, a postdoctoral research at Yonsei University in the Republic of Korea. He did his PhD in School of Basic Science at Indian Institute of Technology, Mandi, India. He is specialized. His specialization is focused on the design, synthesis, and comprehensive characterization of advanced material. And his major research focus area is exploration of diverse material classes, including thermoelectric materials, semiconductors, chalcogenides, oxide, and topological insulators. He has published several research papers in national and international reputed journals. So with this, I welcome Dr. Acharya to deliver his talk, and welcome, sir.
Good morning, all of you. Thank you for the nice introduction. So let me start my talk today. So I will discuss about the high entropy chalcopyrite. So with some distorted nanostructure with improved thermoelectric efficiency. So first I will discuss about the what is the thermoelectric materials. I'll briefly discuss. Then I will start about the what is high entropy thermoelectrics. Then why we choose the chalcopyrite materials, and what is the specialty about our work, like this quasi-random distribution of distorted nanostructure. And then I'll show you some of the results of electrical and thermal transport, and with conclusion. So let me show you first what is thermoelectric materials. Maybe many of you know that. So thermoelectric materials can use the thermal gradients or waste heat can create the electricity from the thermal gradients or waste heat. And you know the heat is everywhere is present, like industry and automobile and the equipment and also the human being. So if we can use the what we can lost is 66% of energy or heat which we lost in the environment, but the thermoelectrics material can use this heat and we can create some electrical energy, and that going to help us in our society. So basically thermoelectric materials depend on mainly the Seebeck effect and the Peltier effect. And for the Seebeck effect, we need the two type of material, like one P type and one N type, the thermoelectric materials. And if we create some the temperature gradient like heat input and the heat rejected, then we could create some power generation. That is called Seebeck effect. And the vice versa effect, if we create some refrigeration, it is called the Peltier effect. So these are the two main things for the any thermoelectric materials. We can use Seebeck effect and the Peltier effect. And what is the advantage if we saw the thermoelectric materials? So we can make some the thermoelectric watches with a very small power, and we can make some thermoelectric body suits, and we make a refrigerator, and we can use the car exhaust engine to make some battery or the source of the power. And also we can use for the space part. So what is the advantage of this use the thermoelectric materials? It is no gas emission, is eco-friendly, and it is maintenance free. So we can notice no moving part, and it's compact and less weight. And the other thing is very high reliability if we use the thermoelectric materials. So then I will discuss that what is the dependence of the thermoelectric materials. So what is the good thermoelectric materials characteristics? So this is the equations called figure of merit ZT here. So its ZT mainly depends on the Seebeck coefficient, that our term, and the electrical conductivity, and also the thermal conductivity, that is contain electron and lattice part. So if we need good high ZT, means high thermal conversion efficiency materials. So we need good Seebeck coefficient, high Seebeck coefficient, high electrical conductivity, and also side by side we need low thermal conductivity. But the Seebeck coefficient, thermal conductivity, and electrical conductivity is inversely interrelated with the carrier concentration of the material. If you see the right side of the plot, if you see the carrier concentration versus the Seebeck coefficient, electrical conductivity, and thermal conductivity, you can see for the highest carrier concentration of this is called the metallic region. In that region, the Seebeck coefficient is very low, but the electrical conductivity is high, thermal conductivity is high. And also, if we go to some normal region, so in the insulating region or low carrier concentration region, you can get high Seebeck coefficient, but the electrical conductivity and thermal conductivity is low. Due to that, the ZT is low here, and also the high carrier concentration region, or the metallic part, also the ZT is low. So for the good thermoelectric material, or for the high ZT material, we need the optimal carrier concentration region, or you can say the semiconducting region. This is the optimal region that here we can get the high ZT of any of the material. And other thing is that the Seebeck coefficient and the electrical conductivity part is called the power factor. This power factor is also high for the semiconducting region. So what is the challenges in thermoelectric materials? The main challenge is that we need high power factor, and also the reducing the lattice thermal conductivity. And the main thing for the thermoelectric materials is that we have to need the decoupling of charge and heat flow for the high Seebeck coefficient or the high power factor, and side by side the low thermal conductivity. So there is some different approaches that we need to tune the carrier concentration, or you can say, for the high ZT materials. Like one is the doping and alloying. So, and also the nanostructuring and low carrier energy filtering for the reducing thermal conductivity. And so second phase introduction to reduce the thermal conductivity. And the phonon glass and electron crystal, these are some of the approaches for the high ZT to tune the carrier concentration of the material and the low thermal conductivity. And there's a plot you can see basically with the evolution of the ZT with the year. So previous times we got only the 0.5 or 1 only, but the recent time after the 2000, this ZT is enhancing with different kind of materials. So we have introduced, and also using some of the techniques that I already talked. So we can get around ZTS3 if in the near future. So what is the technique to means enhancement of the power factor? So this is one of the technique is carrier concentration optimization, and one of the modification of electronic band structure. So carrier concentration optimization is there is a electrical conductivity is depend on carrier concentration and mobility. So if you tune the carrier concentration, or you can increase the carrier concentration, so you can get some high electrical conductivity. And side by side, the Seebeck coefficient is depend on the effective mass and the carrier concentration. So if you decrease the carrier concentration, you can increase the Seebeck coefficient. And also if you increase the effective mass, this is MD, with the band's energy, or you can say the band engineering, then you can get the high Seebeck coefficient. So that can help for the high power factor of any thermoelectric material. And another thing is that, so reducing the thermal conductivity, I already took the thermal conductivity can reduce with some multiple phonon scattering and increasing low thermal conductivity. This lattice thermal conductivity mainly depends on three parts. This is specific heat and phonon grip velocity and phonon mean free path. So for if we choose some high complex crystal structure that can use for the low specific heat, and for if we create some enharmonicity in the material, that is also help us to low the phonon group velocity, and that can help for the low thermal conductivity. And other thing is that you can if we use some multi-scale phonon scattering, then you can enhance the phonon scattering, and that phonon scattering reduce the phonon mean free path, that will help the low thermal conductivity of the material. So then I will start about why we choose the high entropy material. So basically, high entropy is that normally we use only 2 compound material or 3 compound material. But if we increase the number of component of the material, if you see the plot, so if you increase the number of component, you can increase the configuration entropy. And if we increase the configuration entropy, what we see, we can get some good stable structure. So these are plot of the Seebeck coefficient and configuration entropy. So these are some example of the reference paper. So here, if you see, if we increase the configuration entropy, your Seebeck coefficient is also increasing little bit. But the main thing, the important thing is that if you see the plot of the lattice thermal conductivity with the configuration entropy, that any material of thermoelectric material, that if you increase the configuration entropy, you can reduce the lattice thermal conductivity hugely. So if we use the number of multiple element, or you can create the more configuration entropy, that it can help us to reduce thermal conductivity, and side by side it can also stable the good Seebeck coefficient. We choose chalcopyrite material. So it's basically 136 group material is copper Ag, and the gallium indium and the tellurium is a mid gap semiconductor. And another thing is that it is diamond like tetrahedral coordinate structure. And the promising thing is that this type of material has very high Seebeck coefficient and decent electrical conductivity. But the major drawback is that this kind of structure or diamond structure has very high lattice thermal conductivity. That is for that you can get very low ZT. So this is the chart of different kind of copper material. And this is some of the chalcopyrite material. You can see the Seebeck coefficient is quite high, but the electrical conductivity is not so high. But the main thing is that the main challenges of the chalcopyrite material is that the thermal conductivity is very high. And due to that, the ZT is not so high. It's around 1 or below 1. So our main challenge is that we have to reduce the thermal conductivity, and side by side, we do not hamper the power factor of the electrical part. So then we start about this copper indium telluride and copper gallium telluride. And first, for the number of increasing the element or increasing the configuration entropy, we doped with the silver in the copper part and also indium in the gallium part. So we create some of the material which in some solid state method. Then for the increasing the configuration entropy or number of elements added, we added the Zn also. So with Zn, we can create the 5 number of samples. If you see the XRD study of our sample, the left-hand side is the without Zn, and the right side is the adding the after the Zn. So all the samples have here the tetragonal crystal structure, and there is no extra phase. So after adding the Zn also, we get very good crystal structure. So, and other thing is that we did some XRD study, and we see that the black one is the parent material. So after adding the material, we get some more lattice strain induced in the sample. So this lattice strain can help us to reduce the thermal conductivity that we can see after that. So then we did the HRTM also. So we see in the HRTM, adding the number of element, we can create some Moir fringes here. That Moir fringes or it creates some nanoscale distortion. This nanoscale distortion can help us to more phonon scattering here. And also side by side for the high entropy materials that we use number of elements, that number of elements has different kind of mass, that also creates some atomic scale distortion. So in our samples, we get atomic scale distortion and side by side nanoscale distortion. That is quasi dimension, that we say this is the random distribution of the nanoscale distortion. So this nanoscale distortion and the atomic scale distortion is also showing in the TEM. You can see some of the Moir fringes you can see here, and also different kind of lattice structure. So that can help us for the low thermal conductivity with the enhancing the phonon scattering, and side by side we create also lattice strain in our sample. So this is some TEM images. So if you see the measurement plot of the total thermal conductivity with the temperature, this is without Zn sample, and the right side is the Zn sample. So you will see the parent material has very high thermal conductivity at the room temperature as well as the high temperature. But after the number of element increasing or the doping, you see the thermal conductivity is decreased. But and also with the Zn, the thermal conductivity or the total thermal conductivity is reduced very low. We around 0.38 for the after the adding the Zn, or you can say you can adding the element or more configuration entropy. So this is the plot of the lattice thermal conductivity with the room temperature and side by side the high temperature. So we see that after the adding Zn, we get very low thermal conductivity, and we also analyze with some TFT also. So we see there is a more phonon scattering of the density of state, and we get some low group velocity. So we also try to fit our thermal conductivity with some mass scattering and phonon scattering, and also the introducing extra term, strain term. And this fitting is also matches with our experimental result that can show that our material has some strain and also phonon scattering and mass. Due to the mass difference, the thermal conductivity is very low. And Also, we'll see the electrical transport. If you see the electrical transport, this is the carrier concentration, and the right side is the mobility. That this is the without Zn sample, and this is the Zn sample. So you see the after the adding the doping or number of element, the carrier concentration is increasing. But after the Zn, the mobility is decreasing. That we know that we are high entropy sample, that it can decrease the mobility. But the the electrical conductivity and the Seebeck coefficient is not hampered with the adding the number of element. So what we see, the temperature dependent also see the mobility is decreasing, carrier concentration increasing, which supports the electrical result. And if you see the power factor is with the this is the parent material, but after the doping, the power factor is enhanced, and Zn also after adding the Zn, the power factor is not degraded much. So due to that, we get low thermal conductivity and high power factor, and that help us to create the high ZT of the material. If you see the ZT with the temperature, that without Zn and Zn sample, the pure materials is ZT around 0.6 at the high temperature. But after the adding the number of element like silver and indium, we create 1.2 at the ZT at high temperature. And after the Zn, means high entropy sample, due to the low thermal conductivity and good power factor, we reaches at 1.56. It's very huge for the ZT at the high temperature. And if you see, there's a plot in the upper side, there's this increasing the confluence entropy, and side by side we create the high ZT, and the low thermal conductivity is the blue one. So if we see, these are parent material, the ZT is 0.59 to 0.6. But after adding the number of element, or you can see the increasing the number of element, like adding the confluence entropy, our ZT is enhancing to 1.56. And it is 132% of enhancement of the ZT. So in the conclusion, what we can say that we create some unique distorted nanostructure that help us to configure the entropy, increase it, and also it creates some lattice strain, and that is also proven in the DFT and our TEM images. And that also help us to the more further phonon scattering that can reduce the thermal conductivity. And that's why we get some high ZT at the high temperature material. So this is published in the Nano Energy in last year. So at last, I conclude my talk with the acknowledgement, and thank you. If you have some question, please ask. Yes.
What is the limit which you want to reach to have this commercialized?
I'm sorry, can
Of the figure of merit.
Yes.
What is the target to achieve so that it can be commercialized?
Yeah, now is commercial is very low power of instrument, like we can use some watches and like small fridge, and also some kind of device like medical device that use very small power. But if we reach around three more than three, that I think it can help to use more power. We can use more power. So ZT3, I think nowadays people are researching to reach the ZT around 3.
Thank you.
Yes. Yes. So for the thermal conductivity, we measure the diffusivity for the thermal conductivity measurement. And for the thermal conductivity, we need diffusivity with Seebeck coefficient and also the density of the material. So if the samples increase more number of porosity, or you can say that, I think it decrease the density. And so if the sample low density samples can create low electrical conductivity, but our sample electrical conductivity is not so low after the doping, or you can say the material. So we generally we do not measure the porosity, but we measure the other part like electrical conductivity and other thing, and density also. Yeah. Yes. Carrier concentration. Yeah.
So what will be the effect of if we play with the anions, like if the tellurium is replaced with some other chalcogenides and tellurium is added as a dopant.
Yeah. But in this sample, if chalcopyrite sample, so we do not touch the tellurium part here because maybe in that thing the carrier concentration maybe decrease or maybe not optimize carrier concentration. We want to reach some optimal carrier concentration.
Okay.
So sometimes some other material also they used, like in the place of tellurium they use selenium and sulfur, maybe they can use. But in this particular sample, is I think if we
I'm not this particular sample. In general, if we play with the sulfur and selenium,
Yes,
the same effect will be kind of this thing or-
not same effect, means our motivation is to that we can get optimal carrier concentration region, like the semiconducting region, to get good ZT of the material. So maybe some of the materials has some properties there. You can tune the tellurium part or the anion part, I think.
Thank you.
Thank you so much, Dr. Somnath, for the wonderful talk. Now it's our pleasure that in this session we have two speakers in physical mode from two different renowned labs. So now let's welcome our next speaker of the session, Dr. Pratap Vishnoi. Dr. Pratap Vishnoi is working as assistant professor in New Chemistry Unit and International Center for Material Science, Jawaharlal Nehru Center for Advanced Scientific Research, JNCASR, Bangalore. Dr. Vishnoi has done his PhD from IIT Mumbai. Earlier that, he is a recipient of prestigious Ramanujam Fellowship and many more. He has published several number of research papers in national and international peer-reviewed journals. With this, I welcome Dr. Pratap to deliver his lecture. Let me do it. I have to share it also.
As I can help. Committee. Suggest a minute.
I think, ma'am, Dr. Somnath needs to unshare it first.
हाँ वही किया है। ये चला गया क्या, बाहर हो गया क्या? Sir, where? Sir, up. Where is your?
Just in pen drive.
It's okay. Document. It's in your pen drive.
Do I need to call some IT fellow? I think they're not able to.
Here it is. Wait.
It's in USB drive.
Yeah. This one, MET 20
Yeah, that's right,
September.
yes. Yeah, that's it.
Okay.
It is not sharing. It's a simple technique. Share to it's a simple thing. Why it is not sharing?
You go open, I think.
No, it's open. It's open.
If it is open.
You just have to. Okay, let me.
Maybe you have open.
No, not this one. Wait.
Yeah.
हो जाएगा सर.
Is it Google or?
शेयर करना. ओपन है
ऐसे नहीं मैम,
यहाँ
ऐसे
से ओपन कर रखा
ये है ना।
कर रखा वही कर रहे थे
सॉरी।
ये तो हम क्लास में हमेशा ये इसको बोलते हैं।
So let me thank the organizing committee for inviting me to speak here. Um, so in this meeting, I'll be talking about halide perovskites or magnetic materials. I believe not all, maybe some of you are aware about halide perovskite as solar cell materials or optoelectronic materials. This is slightly away from that path. We of course work on solar cell related halide perovskite as well, but today I'll be talking about some of the magnetic halide perovskites. So just to give a big picture of what we do in our group at Bangalore. Sorry. So we work on a few aspects of largely metal halides. One of them is the semiconducting halide perovskites. And the fraction of group, some of the students are involved in magnetic halide perovskites, in which we make conventional magnetic materials, along with we are more interested in the quantum spin liquid material, which is the next generation, the computing, the supercomputer material, the quantum materials. And then we also look at phase change material, which is basically material where a material can absorb energy, change the structural phase. You can carry energy from this place to the other place, and then you can reverse that to release the energy. So basically, through the phase change materials, energy can be stored and transported. And of late, we also working on light emitting material. These are all largely metal halide materials. Some of the pictures are shown here where this particular material shows the quantum yield around 70 to 80%. So in the today's seminar, I'll be talking about metal halide perovskites as magnetic material. So before I go in the science that we do, I just thought of giving a very brief introduction about magnetic materials. So in physics or chemistry, we studied when we apply current to a conductor, when electrons move, they generate magnetic field. But that is a different thing. This is the material which is magnetic inherently. It's not because we are flowing current, because of that it becomes magnetic. No, it is magnetic because the atoms, some of the atoms or all the atoms that are making the materials are having half-filled orbitals with electrons. So basically you have orbitals in the atoms, some of the atoms in the material, in the crystal, which have unpaired electrons. In orbitals, typically in orbital, you occupy 2 electrons, they will couple in the opposite spin and cancel each other. But in this case, it should be half-filled. So such materials, when you place in a magnetic field, they respond to magnetic field. So this is the kind of material I'm going to talk about. And of course, their applications are very old, but the upcoming application, like the memory devices and so on. But one of the very potential upcoming application is spin electronics, where you have materials which are already known to be semiconductor. In the semiconductor, we look at the charge on the electron. We don't worry about the spin. But when you club spin with the charge, it becomes spin electronics. That is the upcoming technology where a lot of research across the globe going on. So if you take metal halide, which are known to be semiconductor, and then in that you have magnetism introduced, so this could be a potential material for spin electronic related applications. So here I given a picture where you have electron, some of them are up spin, some of them are the down spin, and we can compare them with a permanent magnet which has north and south pole. So you can consider up spin electrons as north pole and the down spin as south pole. Well, so that's the how material become magnetic, but the magnetic material is interesting only if the neighboring atoms, which are carrying unpaired spins, couple with each other. So there should be a magnetic exchange. If that is not there, then they're uninteresting. There's no interest in those materials. So just to give a brief picture of how the magnetic materials behave when you put them in magnetic field. So they could be paramagnetic. Each of these arrows is showing unpaired spin on an atom. They could be randomly oriented with respect to each other. We'll call them paramagnetic. They are not often of interest. Then the spin on the neighboring atoms can couple antiferromagnetic up and down to cancel the holistic magnetic picture. So they are the antiferromagnetic material. There's a lot of interest in these materials because the point at which this spins antiferromagnetic couple at the temperature, that's where, you know, that behavior changes. And they all can be in the same direction. There's a ferromagnet. These are fairly old phenomenon. But what is happening in these materials, in all of these neighbors are kept, you see there's a square lattice. And this process, what I'm showing here, it happens when the magnetic atoms are forming a square lattice or a cubic lattice if you talk about 3D. But there's one more thing. If you don't have square lattice, atoms are placed in such a way that if you connect the neighbors, they form triangle. This triangular, when it comes in the picture, you cannot ever cancel. If it is a material is antiferromagnet and the lattice is triangular, you cannot have ever a fully antiferromagnetic system because if you look at the picture here is up spin, this is down spin. So along this line is antiferromagnet. But in this line, you can make it antiferromagnet by putting the spin down. But then if you see spin up, sorry, but then you see this up spin and this up spin, there is ferromagnetic interaction. So in such system, there's always fluctuation. This spins always will fluctuate. It's called quantum fluctuation. And such materials actually, one of the potential material for quantum is spin liquid. There's a quantum computing materials. There's something which is upcoming in future technology. So this is one of the very important magnetic material. That such material is called frustrated magnets. They're of there's a lot of research interest currently going on, as well as the applied interest in applied area. So this can be, you know, it can be of next level. We put couple of more triangle, make this kind of a structure where again you cannot cancel each other. You are basically increasing the frustration to the next level. I'm writing here 8 equal energy states because when it's fluctuate, it can be up or down. Each corner can behave like this. There are 4 corners. So 4 into 2, you can have 8. In the previous case, you can have 6. So we see there's more than one. There's a degeneracy. As long as there's a degeneracy, fluctuation will continue. But in a perfect antiferromagnetic system, you will always have only one state. So thus, these kind of system, they will never find a single ground state at any temperature, ideally. And that's where they become very, very interesting system. So with this brief introduction about magnet, I'll just briefly say how we measure magnet. We have a magnetic material. Then how do we know whether this magnetic material is antiferromagnet, ferromagnet, or a frustrated antiferromagnet, and so on? So we simply take material, put in this squid magnetometer, and measure the magnetization. This is nothing but the response that material gives us when you put them in magnetic field. And so we measure magnetization and then analyze data using this magnetic susceptibility. And typically we use this kind of equation to find out what is the strength of magnetic interaction. We want the spin to be interacting very, very strong so that the phenomenon that we are looking for is quite strong. And then you can, of course, analyze them and say whether it's ferromagnet, antiferromagnet, or a paramagnet. So I will not go in the details of this. We can find out from there, but we can discuss more if you are interested. Okay, but let me now go to the material that we use for looking at magnetic properties. So we look at the derivative of halide perovskites. So this is a fundamental structure of a halide perovskite, where each octahedron that you see blue color has a metal at the center, and there will be 6 halide on the corners of this. All the corners, they form 3D structure. That's how the perovskite framework form. And this framework is very, very important material framework for semiconductor application. And then in the cavity, you can fill some cation to charge balance. But however, the material which I'm going to talk about are the derivative of this fundamental unit, which are called double perovskite, where what you do is the 2 neighboring polyhedra, you have different metals. One of them we are keeping magnetic metal, other one is non-magnetic metal. And these, so because there are 2 types of metals, you call them double perovskite, but they can be corner shaped 3D structure. But a few years ago, we discovered that they can also make 1-dimensional chain magnet or 1-dimensional material. So with this, let me give one of the example that we recently developed, I think, a year or 2 years ago. where we have magnetic metal, which is molybdenum, which has is a moderate magnetism is there, because if you look at magnetic molybdenum in 3+ state, it has 3 unpaired spins. So 3 unpaired spin is quite a bit. And then the atoms in the neighbor, they couple, in this case, antiferromagnetically, but there is something very special about this. If you see in this structure, the molybdenum atom, which are the blue one, and if you look there, connect them, you see there is the tetrahedron forming. And this is the one of the structure with the characteristic of antiferromagnet, frustrated antiferromagnet, which I just mentioned. And here we find there is a frustration. So in this case, the magnet, the unpaired spin, they do not completely cancel each other, because where they are kept, they have to be frustrated. So we see the frustration along this edge, and also the edge which is behind. And how do we find out? We find out from these parameters. So if it is a perfect antiferromagnet, you will get the Curie-wise temperature divided by the nail temperature equal to 1. But when it increases, any value above that indicates a frustration. We have around 5. It's moderate, not very high. But there's a sign of frustration here. So this is one of the potential materials for quantum spin liquid behavior. But then to do a control experiment, this is a stability, so I'll skip that. Of course, this material absorb actually around 2 eV, which is close to 600 nanometer, and the wavelength below that, which is actually, is not a great band gap, but it's really good. For the solar cell application, the band gap criteria is around 1.4 or so. That means that absorbs full visible UV and some part of NIR. But this absorbs half of the visible and UV portion of the light, and it's very stable over weeks. Yeah. So, but then coming to, as I mentioned, they could be 3-dimensional, but a few years ago we shown that they can be 1-dimensional chain as well. You see the polar kind, the pole type of chains are forming. There's no 3D connectivity. So these materials basically 1-dimensional material, low-dimensional material, but is not nanostructured, meaning we are not taking materials and reducing the particle size to nanorods. No, these are bulk crystals, but within bulk crystals, you see nanorods, which are separated about 7 to 8 angstrom by organic stuff, which is methylammonium in this case. This is methylammonium cation here, which is actually between the chains. So in this 1-dimensional magnet, it has the frustration part is gone. You see there's a, I think the frustration factor is around 1 or so, but it still orders very, very poorly around 2. So this is not a good magnet, but it's as a proof of concept, you can see when it's not 3D, the frustration, of course, not there. But we did something more on this of late. This is here we have the so one of the aspect of the magnetism which I just forgot to mention is, because this material I mentioned, they're ordering around 3 or 4 Kelvin. That's very low, and is of course a challenge how to bring this temperature closer to room temperature. We have to basically this indicates the strength of the magnetic exchange interaction, but the strength how we develop inherently in the material. So that means we have to do some design strategies or the structural changes so that temperature can be brought closer to room temperature. So one of the thing that we did here to change the metal in between the molybdenum ions, that is silver in this, sodium in this case, from silver to sodium, when we change, the temperature change from 2.3 to around 5, between 5 and 6 Kelvin. So there are about 3 Kelvin shift. But otherwise it is similar to the previous case structure-wise. Okay. Not only that, but then you can change the distance by changing the halide size. That also you can make bigger. So instead of chloride, you bring in a bromine, and that further shifts the magnetic temperature. And we clearly see a trend when you change the sodium, it goes to 5.2 Kelvin from 2.3 in the case of the silver here. But then we change from chlorine, pure chlorine, to keep on mixing bromide, that is the larger atoms. And here on the rightmost side, you have the highest amount of bromine, but you see the temperature again increased by a couple of Kelvin. So this is basically when you add more bromine, of course, the effect, what you expect is should be reversed because you are sending molybdenum atoms away from each other. So the magnetic exchange should decrease, but that's not the case. What we see is with more and more bromide, bonds become more and more covalent. So that leads to stronger magnetic exchange interaction. And so does the stronger, the higher Nile temperature, the temperature at which the magnet become antiferromagnet. So here is the summary of this, the one-dimensional system, which we met several. So, the thought of comparing them, how they look like. So you see that we can increase temperature from very close to, lowest temperature where we can go practically, that is 2 Kelvin, to all the way to 7 Kelvin, just by tuning chemical ingredients of these materials. But structurally, it's all are similar. So here is one of the very new within this one-dimensional system we did. This is not magnetic. I'll take 1 or 2 minutes on this. It's a very recent result. So what here we did in the one-dimensional chain, instead of molybdenum, we brought on indium, which is one of the lead-free alternative in halide perovskite, where people talk about lead-free halide perovskite. When you talk about lead-free, means you have to think about alternate metal. The indium is one of the potential candidate for that. Also, other one is bismuth and so on. We also work on those areas too. Okay, so here when indium comes in, it becomes non-magnetic, but the purpose is not magnetism here, of course. And then the material alone is uninteresting. What I written here is neither magnetic nor it is optoelectronically active, because its band gap is around 5. That means it's only absorbed in UV about 300 nanometer or so. So to make this metal interesting, we take a crystal of this compound, is here, just dip in a solution which has antimony cations, just dip and take crystal out, put in UV chamber, you see it glows like anything. You see it, and a whole chamber glows with about 60% quantum yield and so on. So what happens is some of the indium, 1 or 2% indium atoms are replaced by antimony atoms. And that leads to this highly emissive materials. So this is, again, one of the very first report. We submitted it just a week ago or so for publication. Hope to see this online. This very first report on the one-dimensional chain, highly emissive materials with, there's no lead, no toxic element. All are, these are benign elements. So more is going on this area as well. So this is called antimony doping induced photoluminescence. So this is slightly deviated, the higher dimensionality. Before I close, I'll just briefly just want to say about this. This is the phase change materials. How we make these materials phase change. So this is a 2-dimensional layer, you see. I won't go in the details. So this is a 2D system. There's a gap in between 2D, this perovskite layer. You see this here. These are all organic amines. These are the formula here, the structures here. Now, these amines are very flexible. This is a butyl chain here. You can heat it or cool it. Because it's flexible, it changes its arrangement, atomic arrangement. And that leads to phase change. In this case, around 160 degrees C. So what does it mean is, you take this metal, make wherever you are, heat it to 160. And then if you're able to keep it at that temperature, you can transport this metal some other place and then cool it down. So around 147, there's about 12 to 13 degrees C, there's a hysteresis, but that's okay. You cool it down, that heat will be released. So such materials are again potential materials in energy storage and transportation. So yes, so this with this I'll conclude that I hope I convinced some of the unconventional halide perovskites with showing the known properties, and for example magnetism, which is known for about centuries. So the such property we are seeing in the new kind of materials, and then also the photoluminescence, and then looking at various properties by changing materials dimensionality without doing nanostructuring. Nanostructuring is nothing but the nanomaterials, where you take material and somehow make the particles of small size. But here, all these are bulk crystals or bulk thin film. But because the atomic arrangement is such that within the crystal, you have chains or seeds which are actually nano size. So yes, the work we do, without support from various sources, we cannot do. So let me thank them. So we have group about 7 to 8 students, and the work which I just mentioned is largely by Devesh and Ajay, and some of the previous postdocs, the Khyati and Prasurya. They both are left my group. Prasurya is now faculty in Dibrugarh University. Khyati is doing another postdoc in the United States. And of course, we collaborate with Professor Panpati's group to understand what is going on these systems. There are a lot of physics, and we are chemists, so we always look for collaboration to understand the thing. And the facility that we use, it's called Samat facility in JNCSR. So we are so grateful to them. And of course, funding from different sources. And I'm particularly grateful to SERB because that's where I started independent career as Ramanujan Fellow, later become regular faculty. I've also have core grant from SERB. So thank you all for your attention. And I'll be happy to answer. Yeah, so this we use, yes, actually it's a really good question. This question only one of the paper 3 or 4 years ago we did, or that where we first time we found that why particular composition makes a one dimension chain. That was 2020 around we wrote that. And then when I was in for second postdoc. So it is for perovskite, there are a couple of geometrical parameters we calculate. One of them is called tolerance factor and the radius ratio. So we have a very good hand on that. So we do calculation before. And often, so far, my experience is based on the calculation, when we try to synthesize, we get the right dimensionality. So we can talk about that more, the calculation. Yeah, yes. Otherwise, heat and trial, we are a synthetic chemist. So with several failures, it will be trouble. Mm. We mix the ingredients in the ratio that we are, hoping to make. And then whether that has happened, often that doesn't happen in that ratio. But then we do a high level characterization to find out what is the ratio that we got. So the sum of the ratio is not what we planned. That's how because if you have seen, the numbers are in fractions, but that's not what we planned. The reason for what it doesn't happen the way we want, because we exactly don't know what is the reactivity of bromine and chlorine. We don't know exactly, but surely there is a difference. So that the inherent difference leads to what ratio it is versus what we actually, planning to make. So there is always some differences there. But of course, we have a good control on dimensionality, materials type. There. Oh, which method we use? So these are all what I mentioned as are the based on high quality single crystals. We make them by heating the ingredient metal. For example, if I have to make, sorry. No, it is in solution. What we do is very simple. We take, for let's say indium last compound, we take indium oxide, we take methyl ammonium, that amine is commercially available. And then I think sodium was there. So we take sodium chloride. All together we put in hydrobromic acid, commercial one. Just put and cook it. But then you cool it. That cooling step is very, very essential to get high quality crystal. So we cool it very slow. I think it is over 2 days or so. From the highest temperature we try to reach at 200, but then cool to room temperature over 2 or 3 days or so. Crystallization, and the crystal quality depends on how you tune that. So, but the halides all we don't add from outside. If we want a chloride to be made, we take commercial hydrochloric acid, just dump in that.
I have one more.
So frustrated are actually they're antiferromagnet. Yes. For ferromagnet, frustration doesn't apply because ferromagnet means all spins are up or down. So you can put all up in whether it is a triangle or whatever it is, all up or down, not an issue. It becomes frustrated when the corners are odd in number. So you cannot satisfy up and down. Yes. So it's basically geometry. But then challenge is how, because synthesis is a challenge, is not easy thing. How we can make material where the magnetic atoms are arranged in the way the geometry suggests. That's where we work. With geometries and the frustration, the concept is known for maybe centuries, I think. Yes. But then it picked up this recently because of quantum computing. If you have this kind of material, if it is magnetic, it will fluctuate. Ideally, it should fluctuate even at 0 Kelvin. We cannot go there, but it should because geometry is such. Yeah. Yes, it's again excellent question. Yeah. What we do is this. So these are bulk crystal. I mean, it can be centimeter big also. But within that, there are chains which are separated large by 10. We can separate them by 10 angstrom, 20, all these things we can do. So if your separation is that large, let's say chains are like this. And if we measure the conductivity perpendicular, if you don't find a conductivity this way, that means electronic conductivity is not there. So confinement has happened. That is the nano behavior. Yes, nano realms. Yes. So basically you are confining them. Yeah, we do control experiment to find out that it's not there because there's a fillers which are non-conducting. Yeah. Yes. Yes. And then the similar behavior you can see in magnet also. When you do magnetism, you should do the anisotropy measurement and see whether there's any magnetic exchange happening. If they're far away, it's expected not to happen. So that means they are confined. There's no communication. And that's what is nano confinement.
Thank you, sir.
Yeah. Thank you very much. Oh, yeah.
So why did you choose the SB with antimony in your samples? And from the XRD, I've seen that there's some extra phases with the antimony, with the chlorine, but not in the bromine. So
Bromine also, in both are there.
extra phases,
Oh, in the
XRD.
can you please repeat the question?
So why did you choose the antimony in your both the samples like chlorine and bromine? But I've seen in the XRD there is some extra phases with I think in the SB. So
Yeah, that's extra phase is nothing but is in one of the samples sodium chloride impurity is there.
this is sodium chloride.
Sodium chloride, but our measurement, because one way you can separate it, but because these crystals are colorless, actually there's a huge stock shift. So if you do UV, this doped system, they absorb around 300 nanometers also. That's a UV. Sodium chloride is also UV, but sodium chloride is not emissive. So we are not bothered to remove that. Yeah, but the emission that I shown is chloride is not that emissive. It is a bromide sample. So there is some reason we are still digging into it, why chloride didn't show emission. But then the reason for using antimony is that antimony, when you dope, it creates another level between the band gap. And that level, the electronic transition which were forbidden in indium because of parity are now allowed. So the allowed transition gives the emission.
Okay, and I think that continue the same question. So you choose the bromine 1.41 and something. So I think the same answer that you.
Yeah.
Thank you.
Thank you. Thank you very much.
I think we will entertain more questions on during tea time. Thank you so much, sir.
She has one more, but I'll talk to her. Yeah.
Lucky.
Yes, that's I'll talk to her later.
Okay, even the student have few questions, I guess. Avi, we will discuss it during tea time because our next speaker is waiting. Thank you so much, sir, for a wonderful talk. So with this now, let's welcome our third speaker of the session, Dr. Fauzia. Dr. Fawzia is an, ma'am, are you here? Can you listen me?
Yes, good morning, dear.
Yeah. Good morning, ma'am. Yeah, Dr.
Good morning.
Fawzia is an associate professor and head of physics, Department of Maulana Azad, National Institute of Technology, Bhopal, India. She has received his PhD degree in physics in 2007. She has guided more than 20 students in PhD and published numerous number of research paper in peer-reviewed international and national journals. With this, I welcome Dr. Fawzia. Ma'am, please share your screen is already shared. Ma'am, the platform is yours.
So I think it is visible properly now because
Yes, ma'am. Keep it in a full screen mode. Yeah, it's visible. Just keep it in a full screen mode.
thankful to all the organizers. Maybe you will be listening, my throat is having some conjunction. So I hope the audience and the students will be listening properly.
Ma'am,
I'm
please,
having some throat issue. So
ma'am, please keep it in a full screen mode.
uh,
Yeah, it's not in full screen mode, ma'am. Just make it in a full screen mode.
full screen.
Slideshow mode.
But
Yeah.
on my screen, it is seen that.
No, it's moving, but it's not in a full screen mode, ma'am. Ma'am, go to your PowerPoint presentation and
Yes, I did from itself only. मैंने वहीं से किया है लेकिन अब हो गया?
नो मैम, अंडर स्लाइड शो में मैम एक बार देखिए स्लाइड शो मोड में. हाँ मैम F5 प्रेस कीजिए.
F5 ही कर रही हूँ लेकिन
टॉप में
मैं फिर से शेयर करूँ?
हाँ मैम एक बार कर लीजिए.
Because the screen is not properly visible to me also.
चलने दें. एक मिनट मैम कर रहे हैं.
I'm sharing you and then I'm sharing the slide again.
Okay ma'am, if it is not मैम आपके उसमें 100 चार्जिंग का जहाँ पर पॉइंट है उसके बगल में देखिए एक आइकन है ऊपर, उसको क्लिक कर दीजिए मैम. इट विल वर्क. लेफ्ट हैंड साइड आइकन just in your PowerPoint mode only. Otherwise you continue ma'am, it's okay, no problem.
Is it changing somewhere?
अभी आप शेयर कर रहे हैं वापस से. Yes please ma'am, do it.
अभी now tell me.
No ma'am, just again
Nothing is changed.
मैम आपके बॉटम में जो एक चार्जिंग के बगल में एक 3 सिंबल्स हैं, on that just click the last one or press F5 in your
हाँ वो
keyboard.
F5 तो मैं प्रेस कर रही हूँ. I'm sorry, this is फिर से.
Control F5 मैम.
So this is your brochure, I think.
No ma'am, in my
just-
screen nanotechnology is visible. Your
एक घंटे बाद. Please, sorry. So let me share.
ma'am, you please continue, no problem. It's visible to us.
बस वो इमेज में थोड़ा सा कभी-कभी ना will not be good.
No problem ma'am. You
Ma'am, do one thing. Your office version is a very old. It's 2007. So do one thing. When you're sharing, na, you just choose the option whole screen.
Yes,
Unshare, and choose the whole screen option.
when I'm sharing,
Ma'am, it's not coming in a presentation mode at our end.
I see that it is not changing or what. तो
Ma'am,
फिर
just unshared.
अच्छा अच्छा
Ma'am,
I'm changing the screen now this
ma'am,
is
I stopped it at, ma'am, I stopped it at my end.
it's not changing also क्योंकि मैं यहाँ से change कर रही हूँ तो I'm sharing a different file but it is not being shared there.
मैम, आपका जो ऑफिस है ना वो पुराने वर्जन वाला है। आप एक काम कीजिए, आप इसको स्टॉप शेयर कीजिए।
वो stop sharing भी मैं check
मैं कर
कर
दे रहा हूँ अपने एंड से, स्टॉप शेयर किया। अब मैम आप जूम पे जाइए, वहाँ पे शेयर स्क्रीन कीजिए। वहाँ पे ऑप्शन आएगा स्क्रीन शेयर का, आपको स्क्रीन शेयर करना था।
share
हाँ, अब उस पे
जब
स्क्रीन
share मैं
लिखा
कर
होगा,
रही हूँ
स्क्रीन स्क्रीन
तो
और स्क्रीन चूज कीजिए मैम आप।
एप्लीकेशन नहीं करना है एंटायर
नहीं,
स्क्रीन अगर करूँ मैं
हाँ, एंटायर स्क्रीन कीजिए।
ठीक है नाउ
अब मैम कीजिए इसको, आप प्रेजेंटेशन मोड में कीजिए इसको।
अभी आप बताएं
यस मैम, हो गया।
हो गया
हाँ
चलो थैंक यू सो
Yes, ma'am.
once
Please
again good
continue,
morning
ma'am.
everybody. हाँ
Yes, ma'am. Please continue. Thank you.
thank you so much for the support uh, I'm here to present my recent work on room temperature optical gas sensing, which is a newer technique, though it was existing earlier, but we have done so many permutation and combination and new device fabrication and testing of some other tools. So I want to present that work in your this ambient MIT conference. So through which we have enhanced the optical gas sensing and recovery time also. So and for that we have got the patent also. I'll be discussing it later. So first, I would like to introduce about the Bhopal is a nice place because you are sitting all the way from different part of India and different part of country. So, Bhopal is a nice place to visit. We are having so many institutes. It is academic hub. So many national level institute here at Bhopal. It's good, beautiful environmental place. And we are having, Bhopal is a cultural and historical center also. So we are having so many cultural activities and cultural centers and historical places also, religious places and cultural places also. This is my institute. We are situated at a small hill, which is around 650 acre. It is green, lush, very beautiful campus we are having. So this my favorite slide. I used to keep it for the sake of my students and to tell about small thing, something about the nanomaterial and nanotechnology. As you everybody knows that the particle which are having any one dimension below 100 nanometer can be called as nanomaterial, and depending on the structure call them different structures. And it is not a recent one, but because has been, we have been traces that the nanomaterials and nanotechnology were existing earlier also. In history or ancient time, we have the traces and historical evidences. These are some evidences I used to keep. Then I used to tell about the applications of nanomaterials and nanotechnology. You all are aware of all these applications. And out of these, some are in development stages. For example, we are working on solar cell and solar cell based on nanomaterials. Perovskite solar cell was distilled water. Solar cell are in the market. And we are using nanomaterial based solar cells. And in my lab, we are working on solar cell, gas sensor, and photocatalyst materials also. So what exactly the gas sensors are? The sensors are the device, as you know, which measure any change in the material in the presence of gas, and that change that we can understand what property of which response is changed due to the presence of gas. So what exactly the gas sensor do two things at the time of sensing mechanism, sensing task. It interacts with gas and its surface and performs surface adsorption. It at the same time it transfers the charges, and it may be ion exchange. Small changes are there at the time of interaction, and these changes we do detect through different technique, different mechanism. And because of these changes, it is transforming some property, and that property is maybe converted in the form of electrical conductivity or optical transition or dielectric constant or refractive index or luminescence. I have taken this picture from internet. There are so many kind of gas sensors depending on the technique through which we are detecting the presence of gas. Actually, exactly what the purpose of the work is to detect a gas and identify it from the mixture of gases. And of course, we want to trace a very low ppm gas, and we want to make it a room temperature and viable to all and easy to operate. So on the basis of which response, as I told you here, that we are capturing the response of material in different forms, maybe in the form of conductivity, maybe in the form of optical sensing, optical change, maybe in the form of change in refractive index or dielectric constant. There are so many changes on the absorption of gas, and that change we are detecting on the basis of detection technique. There are different kind of gas sensors, which are optical gas sensors, acoustic gas sensor, and electrochemical gas sensor. Generally, the gas sensor which we are using, you have seen that traffic signal, traffic police is checking some alcohols on the vehicles, vehicle drivers. So they are based on optical electrochemical gas sensors. We are very simple gas sensors, and they somewhat look like this. This is the prototype of some marketed gas sensor element. So the parameter or the requirement for making a gas sensor is the sensing part is the part of sensor, basic part. From that you need some connection, and then you need some meters to get the data. So on the basis of those sensors, we have two main parts are sensing element, that element you are using to detect the gas, and the second thing is the gas itself or mixture of gas itself that you want to study or to detect. So we need the sensor, and the very well you have to measure, you have to capture the data in the form of sensor response, and how sensor response is how much you are smart, the material is smart to capture the gas, absorb the gas, and respond accordingly, because the gas will be oxidizing, it is giving electron, or the gas may be reducing, it will be taking electron, and giving and taking electron will change different properties. And how smartly the material is responding toward the gas is called sensing response. And how much time it takes to give the reaction is sense response time. And when you are removing the gas from the vicinity of the gas sensing element, and after removing the gas, the sensor shall reach to its original state that is called recovery time. And of course, when the last is the selectivity, sensor should be able to select any gas from the mixture of gas and say that this gas is this much, this gas is 40 ppm, or this gas is 50 ppm. And depending on the process parameters, we keep all these variables are depend on the process parameters, which are which may be temperature. Of course, in recent sensing devices, the temperature plays an important role. That is very crucial for us, and we want to change the temperature. We want to make the gas sensing device at room temperature work on. Generally, all the chemical sensors which are being used in the market are having some heating element in the bottom, and they perform their sensing process at somewhat a high temperature, not at the room temperature, which makes it very inconvenient. But it is so, and it also depends on the gas concentration. How much gas is there? Sometimes the gas sensors are not able to sense lower concentration of gases. So we also keep in mind that we have to make a sense small trace gas also. And of course, these are surface area and film thickness, all these parameters which will be affecting the sensing property or sensing element or the material. For that, we are, and of course, this is because these are some, I have told you that the present chemical gas sensor, chemoresistive gas sensor are having their own issues like temperature. They need a high temperature to perform better. They need a high gas concentration. Small trace amount, sometimes they skip, and it gives a complicated result if multiple gases are present. They are not good enough to select particular gas and confirm that this gas is present. So all these issues were addressed in ENO's gas sensing somewhat. They are using multiple elements instead of one single gas sensor. Instead of one single gas sensor, they were using multiple gas sensor at a time, and then using that multiple gas sensor, they were detecting the gas and analyzing the data. These ENO sensor were also good and having better results in case of selectivity issues. But again, they needed some huge, big platform, big sample size, high concentration of gas, and again the temperature itself. So basically the resistive setup is somewhat like this. These are very, very basic because I have shown very basic devices. Of course, in our lab, we have some sophisticated digital multimeters from Fluke and so this is very basic gas sensing device based on resistive, chemoresistive setup, which is existing at current conventional gas sensing setup, in which you can see that metal oxide film. Here, I want to tell you that to enhance the performance or sensitivity or selectivity of gas sensor. So one, we work on the synthesis and characterization of nanomaterial, preferably oxide nanomaterial. Then we make a small prototype device with depositing metal electrode on top and bottom of those metal oxide nanostructure films. And then we used to connect it through multimeters to detect the change in resistance. At the same time, because it is conventional setup, we use some heating element also. Heater is there to heat the material, and the whole setup is kept somewhat like this, a chamber which is have fixed volume around 1000 ml, and accordingly convert the concentration of gas if we insert it from here. So we generally make measurement in the presence of gas, and we use to evacuate it to measure this resistance of gas in the absence or in the room temperature or environmental gas. This is the conventional and basic structure of gas sensing or chemoresistive gas sensor. And the mechanism is somewhat like this. If we can we have the N type or P type oxide nanomaterials, depending on the oxidizing gas, which is an electron acceptor, or depending on the reducing gas, which is giving electron towards the material, toward the sensing material. Depending on these oxidizing and reducing gas, the resistance increases or decreases in the for N type of sensor, and accordingly they show the response curve. The typical response curve is seen like this. You can see the very basic typical response curve for with WO3 film. This is very basic resistive gas sensing technique, and you can see that we have measured this at 300 temperature and 250 degree temperature. We have, but to avoid, and we have calculated the sensitivity. Very standard formula and data is available on the internet and research community, that the sensitivity of any gas material can be measured and calculated through this equation here, this one only. So simply it is a resistance in the gas and resistance in the air, and from that we can measure the sensitivity, and at the same time with this some modification we can derive the sensing time and recovery time also. So these are the basic setups. I have given a background of so what we have suggested we have used in place of these resistance and instrument everything. So we thought about a new photoluminescence based gas sensor, and for that we have designed, earlier we have kept a simple bottle when we started working on that. So instead of detecting resistance in presence of gas, the gas may be reducing or oxidizing. Instead of detecting the resistance, we have we wish to detect the luminescence, because we already had a fluorometer with us in our lab. So we have designed this later on we have designed this quartz sample holder, you can see, and which in the bottom of this quartz sample holder we have attached a standard cuvette, which is used in FTIR and UV visible and spectrophlorometers compartment. This is a very standard cuvette which is attached to a which is having fixed volume of 500 ml, and we have kept two tubes, one for inlet and one for outlet, and then we have closed it with a cork stopper, and we have another hole here. We have customized a hole here to keep it to insert some other gas if we need. So this is the basic sample holder. This sample holder we got patented last year, but we have filed it in 2015. So this sample holder is also having some facilities. If liquid sample is there, you can directly keep it in cuvette and close it, and then flow the gas. And if it is in form of film, you can diagonally, because we are having 90 degree this spectrophlorometer. So we cuvette, we can insert a film at 45 degree, and it faces the beam of incident from the spectrophlorometer, and you can have the luminescence in presence of gas if you feel a gas from here. And at the same time, you can keep some volatile material. If you want to fix or change or test the volatile material also, this chamber is having a small shelf-like design here. You can keep a small bowl, a small crucible with volatile material, and in the presence of that volatile material you can detect the luminescence. So this simple device was patented, and then we have published some work also recently. So with this idea, we have kept the this sample holder in this spectrophotometer inserted. This is the cap of spectrophotometer, and here we have inserted the sample holder along with the sample, and then in absence of any gas, we take the luminescence spectra, and then we fill the gas in fixed amount, 500. We are not we generally we take 2 ppb, and then from 2 ppb to we have the capacity to up to we have seen the good response up to 50 ppm. So you can see this was our first result. We have kept the sample holder and we have inserted ammonia gas in TiO2 material, nano oxide materials with nanomaterials were there. And we have seen a small change in the emission spectra of the TiO2 nanomaterial. And this was the first study. Then we have gone for so many samples, and we have seen different emission peak. You can see that the emissions are taken for different ppm. This red graph is seen for 0.5 ppm gas. We are using we have used zinc oxide, which was doped with sodium at 2%, and this nanomaterial sodium doped zinc oxide nanomaterial was kept in this sample holder, like here, like this, and then we closed the chamber. We have closed the chamber and inserted the 0.5 ppm gas, and at 0.5 ppm gas, we have taken the scan of spectrophotometer scan of the whole wavelength, and we have observed a decrease in the intensity of gas because of the quenching of trapping of electron by gases, and that electron were not able to give that much emission through radiative transition, and that's why they have decreased the intensity or emission. Similarly, we have inserted a large amount of gases, and we have taken this was the basic study at initial stages. So with these good results, we are motivated, and we have done so many we have prepared so many samples, and keep in mind that this nanomaterial will be giving better results. So initially, right from the first day, we have used nanomaterial for our gas sensing devices, optical gas sensing devices. So because this was very new, so we took time. It took time, and it took around 4 to 5 years to get it published, and it was recently we have published so many papers in good journals. So this was the initial result. Then we have changed some material. We have used copper oxide, zinc oxide composite, and we have seen the change in the emission spectra, emission intensity of those material in the presence of gas. We have taken ammonia. We have the facility of NO2 also, carbon monoxide, and all this. So because we were preparing the nanomaterial or gas sensing element in our lab, we used to characterize them with different basic required characterization techniques also. So you can see this is beautiful copper oxide nanostructure composite with zinc oxide. And I have just pasted the SEM image of that. We have done other characterization also, and we have published this paper. And you can see this is AFM result, AFM images are there. So we have reviewed so many paper, and then we got that this is the result from our lab, tin oxide nanoparticle with which we have used for ammonia gas, and it has it was published and has shown a very fast response. 4 second, it is in 14 second, it was giving response and showing the presence of gas. And then we have used the tin oxide and titanium dioxide composite in the same room temperature pH spectra. You can see how small amount of gas was required to get a better results and in faster way. Again, other resistive temperature, we have taken the chemical technique also, chemical resistive technique also, to compare our data. If they are giving a better results or not, to check whether it is suitable for optical sensing or not. We have taken room temperature also, and at room temperature, it required large amount of gases, though they are performing at chemoresistive gas sensing element, but they needed a large amount and they took longer time to give response, and then again took longer time to recover back at its own original state. So these are some other research work done by other people throughout the country, throughout in the world. And we have seen that the result we got for with our small basic tool were better than the existing one. So initially, for having thorough studies, we started with when V2O5 nanostructure with different doping of tin. We have prepared with vanadium oxide nanostructure with tin doping of this much amount, 0.11 and 1.5 and 2 percentage with bio doping through very basic chemical route technique, chemical synthesis route. These are some sample pictures of the sample which we have used and on the glass substrate for making resistive gas sensor, and we have used a quartz substrate like this, small thin 1 centimeter 9 mm with glass substrate we have used for inserting in the sample holder for luminescence sensing. So these are basic results from this characterization of those V2O5 tin dope V2O5 nanostructures. We have done XRDs, and we have calculated the particle size to see whether the particle size is also affecting the responses of responses toward the gases also. So we have some good results with the particle size also. I'll be discussing. So we have done absorption spectroscopy also usable, and from that, using tau plot, we have calculated the band gap of those materials also, and you can see that with the doping of tin concentration, if we increase the concentration of tin, we have seen that the energy gap is increased from 3.08 electron to 3.31 electron volt, and crystallized size calculated from XRD is also decreasing because of
Sorry
their
for the
own.
interruption, ma'am. We are running short of time. If you could please wind up your lecture.
Definitely, I'm reaching to the main results also. So we have studied
Thank you so much.
surface area also, pore size and surface area and pore volume using BET analysis also. For that particular V2O5 materials doped with tin, and we have these are AFM results. These are SEM FSM results of those materials, and this is the basic first luminescence photoluminescence spectra, comparison of photoluminescence spectra of all those 5 samples to compare the defect or of intensity in the presence of due to the variation in concentration of tin, which will be helping us. Will be next which will help response or recovery time calculation also. So this is the basic main results of the gas sensing through luminescence. We have taken different samples, zinc oxide pure and then doped zinc oxide V2O5 with tin, and by inserting 5 ppm with the increase of 5 ppm each, we have taken the luminescence spectra, and you can see it is beautifully showing the response toward the luminescence also, because it is very common that it is understood that the gas, if the gas is reducing or oxidizing, it will flush electron, and it will capture electron from the bands of material, and then on the basis of the flushing and reducing electron, it will give radiative non-radiative transition in the form of luminescence. So this is very basic physics, and we have taken gas sensing spectra overlapped for different samples. From this overlapping, we have seen that the sensitivity, we have calculated the sensitivity using the standard formula available on the literature. Sensitivity is seen to be good for 2% doped tin material, zinc oxide, V2O5 material, which was around 81%. This was for luminescence spectrum, and then we have taken for the comparison, we have measured the material with resistive gas sensing also, chemoresistive setup. We have kept the same sample recovery time. So on the basis of chemoresistive and photoluminescence based technique, we have tabulated the results and responses. In this, you can see the same sample V2O5 with different concentration, doped with different concentration of tin. If you see the resistive setup and PL setup, you'll find that the PL spectroscopy or PL sensing setup is giving better results in approximately all the aspects. So recovery time and response time is seen to be higher for all the samples, and the best is observed for 2% to 10 V2O5, and so it is showing very fast, rapid response of 11 seconds, and it is recovered in 16 seconds. While the same sample shown 14 per second, though this is very good result in its own domain, but in comparison to these resistive setup, we have better PL sensing setup results. So this is just the comparison for one setup. We have recently published a paper on sodium doped zinc oxide and particle for NO2 gas. So these are the simple characterization of, because we have synthesized our nanoparticle in the lab. So we did these characterization for the material, and then Raman also. Let me know. Let me see if we have. Yes, we have done visible spectroscopy also, and the basic requirement of material is sensing setup is the photoluminescence spectroscopy for all the sample at a time. And from this, we have estimated the energy band also from the tau plot. And we see that the 0.3% sodium doped zinc oxide material has a wider band gap in comparison to the pristine zinc oxide. And
My
these are the
apologies, ma'am. Could you please conclude now?
Okay, sure. So these are the second setup of study, and we have seen these better results, and just for comparison. So these are results, we have published it recently, and these are some references from where we have taken. And thanks to all, these are my students. Neha was working on luminescence gas sensor, Neetu Singh, who got the PhD. They are appointed at different places, nice universities, prestigious universities they are working, and they have done photoluminescence spectroscopy. So that's it from my side. So if anybody have any question, if we have time.
Thank you so much, Dr. Fauziya, for the wonderful talk. Ma'am, we have shortage of time. So if any person have any question, please mail to ma'am or mail to ICST. We will forward your questions to ma'am.
Definitely. And
Thank you so
again,
much
I'm
once.
asking regret for the initial this confusion and uploading and sharing of this slide. But I'm thankful to all the team, right from the chancellors, and then ma'am Ashok Chauhan sir and Atul sir and ma'am Balwinder Kaur ma'am and Namaste sir, Jain sir.
Yeah, I'm VK Jain. So remember me.
Yes sir, Namaste sir.
Thank you very much for this nice presentation.
And the whole team of conveners, right from Abhishek sir and Monica ma'am and Robin sir and of course Ashish. Thank you very much, sir.
Thank you.
Ma'am, just one question by one of our colleague, Dr. Robin Kumar. He has one question. Yeah, please, sir.
Thank you, ma'am, for the nice talk. And you actually told about two type of sensors, that is photoluminescence based and resistive based sensor. My question is, which sensor is better for making a handheld device? One. Second is, what about the selectivity of the materials that you have presented here in terms of photoluminescence and the resistivity? Because you have discussed about ammonia sensing mostly.
We have done ammonia sensing for ammonia and for NO2. We have done for so many gas also. If we are talking about the selectivity, we have better selectivity, but we have not created a database. That's why I was I have not included the data in but luminescence spectra is a fingerprint of any material because it depends on the atomic structure and the environment of atoms and molecules or material. So if you take any luminescence spectra, that means it is showing the fingerprint of atomic structure. So if we have mixture of gases using the database, using the data of existing material,
Network.
same it is very good for selectivity in comparison to resistive sensor. Thank you, sir.
With this, I thank all the speaker for this today's session. Now I request Professor V.K. Jain to felicitate our speakers who are present in physical mode. And thank you so much, ma'am, for your wonderful talk.
Thank you.
Okay.
Thank you, sir.
Prashant sir, Jain sir, and Abhishek sir, Robin sir, kindly felicitate our guests. Thank you, everyone.
Ma'am, there is some internet is. Ma'am, can I am audible?
Hello. Hello.
Mr. Nitin, are you there? Mr. Nitin, please unmute yourself.
First, unmute yourself.
Mr. Nitin,
No response. हमारी आवाज जा रही है. Anyway, Apara Tripathi.
Dr. Arpa Tripathi. She registered for you. Who?
So who will present this?
William.
In physical mode? Okay.
अर्पा की बात कर रहे हैं.
ये physical में करेंगे ना? Dr. Apra will present in the physical mode. Okay.
On the behalf of Arpa. No, लग रहा है. Hello, Dr.
Apara
Tripathi.
Are you there?
Please unmute yourself. हाँ चेक कर लो.
हेलो पुलिस सर, आवाज आ रही है मेरी?
वॉइस आ रही है यहाँ पे आपकी.
आ रही है ना? ठीक है सर.
Hello participant, are you listening? Are you getting our voice?
Yes sir, yes sir.
Yes, sir. Yes, you are audible. You are audible.
Why people are not responding? And you may mute all of you, please.
Yes, sir.
So Shreya Gupta, are you there?
Yes, sir.
So please share your presentation first.
Share your
Sure,
topic
sir.
is IT-enabled visitor management system, a secure and efficient
Yes.
application.
Right,
Please share your
sir.
slide
I'm just sharing my screen.
दो है ना?
and make it full screen.
Okay, sir. Sure.
ठीक है? दोनों हैं.
Mhm. Okay, so is it visible?
Yeah, it's
it is
visible.
visible.
Make it full slide.
Sure, sir.
Yeah, Gupta.
Like,
Number.
is it visible, sir?
Yeah, it's visible.
Okay. So good afternoon, one and all present here. I hope I am fully audible. I am Shreya Gupta, a final year BTech student at Amity University and the founder of Digital Divine. Today, I am here to represent one of my ongoing research ideas and to establish a connection between information technology and semiconductor technology. First, to reflect upon my idea, IT-enabled visitor management system deals with a crucial aspect of any organization, say it be university or a corporate office, which means the security and the efficiency of the on-premises. With the advancement in today's technology, where AI, ML, and cloud technology is on peak, with the growing budget in the increasing popularity of the semiconductor technology as well. IT-enabled visitor management system becomes the increasing popular idea, having better visitor experience and secure your official environment. The idea aims to have a smart campuses with digital systems. Now let's first address the hassles we see in the conventional method these days. First and most important is security, as the conventional method of data entry by visitor, that is usually done by our security guards or the officers sitting at the gate, access them in the concern to be raising high these days. Hassle of verification and register entry, as well as we need to approve from the authorizer whom they need to meet, all these sources among these whole process. Allowed zones. Well, this concerns the privacy of the premises. As an outsider, you are not allowed to access all the zones. With the help of GPS and RFI technology, it wouldn't be possible. With this becomes the concerns as well as in conventional methods of the visitor management system. However, to address these, we have a hassle-free entry system that precisely underlines the semiconductor technology, artificial intelligence, and information technology and cloud technology. Compromising all these facilitates the idea of a better visitor management system, which offers these key features as you see on my poster. Digital check-in appointments. Before visiting, the visitor can check in through their details, call for an appointment, and can also verify the details as well as the link with the DigiLocker. So as we link our application with the DigiLocker, there is no case of spy or any unauthorized person to come home. Second, biometric, where semiconductor technology plays a crucial role, as we already have existing chips in the market for face recognitions, fingerprints, or even the sensors we have in the airports. This plays an important role to verify using the same application with their fingerprints or face to replace the manual verification process and allow the person to enter the premises. Using RFI technology, that is radio frequency identification, the GPS will be enabled, that is a built-in system application. Also, you will receive a token as soon as you enter and would be activated using the application, so that it gives the authority to your authorizer to track whether you are under the premises or if you are not undergoing the restricted area. Second one is automated notifications, as authorizers can get alert systems with the visitor tries to get into the restricted areas or step in before the allotted time. So it keeps you tracked or it keeps you alert-based system. It gives you notifications if something is wrong. The application is simple to monitor and helps you with manual and help desk guide within the application when you need any help. to have a look at my graphic on the poster. If you see the prototype design I have designed in the second image, you'll see that it's a very simple basic prototype where it says hello visitor. You can book your visitor's appointment. So this portal would be by the organization. For example, whether it says a university or a corporate field, whether you get services of a new visitor if you are visiting for the first time. Authorizers need to also mention their details. There would be authorizers based on certain designations you have in your organization. Intern visits are also specified since new interns are coming up monthly or weekly. So they would also have an access to the database, and the track is mentioned background. Security is linked with this application as well, so that if the alert is given and the authorizer is not available, even the security have access to all these alert bases. Your new appointments will be visible to you with the name of the person you are visiting, the designation of the person, the time you are
Try to
visiting, and the
conclude.
date. And it would be confirmed or declined. You will get that notification here on the app itself. With the help of help guide, you can see why we are accessing DigiLocker, why we are linking your GPS technology. So these are the guides that will help you monitor through the application as well. And below, lastly, you'll see a high profile. So these are the profiles that are linked to the application, that are linked to the organization. Appointments, inboxes would be any alert based.
Please try to wind up in a minute.
Sure, sir.
Please try
So
to
all
wind
of
up
these
in
are
a
fully
minute.
beneficial in closed organization and monitoring system, having certain benefits of enhanced security, improved data management system as we link it to the cloud system on the basic database, and chips. So that is easily customizable these days. So with these key features and benefits, this system is an ideal solution for organization of all sizes. We believe that system has a potential to revolutionize the way organization manage visits, and look forward for the further discussion on this.
Ma'am.
So yes, sir, here I conclude my presentation.
Shreya, can you hear me?
Yes, ma'am.
Okay. So you have developed this system in which software?
Ma'am, we are developing this system based on the coding we are using in the Python, and we are linking it with a cloud system to have its database at the background.
Okay. How you have implemented the security? Because you have written it is a secure and efficient. So security.
Yes, ma'am. We
your
are using
program is
McAfee.
secured. Program is
Ma'am, we are using McAfee in the application. So McAfee is also going to sponsor us once we are ready with the whole prototype, so that we get the whole security, whether it is for our database, whether it is our security for the visitors' data, DigiLocker. So DigiLocker itself is a secure system. And if we are taking data of our visitors, of our interns and authorizers, we are securing it using the McAfee.
okay. You spoke several times about semiconductors. So how semiconductor is related here?
Absolutely right, ma'am. So semiconductor technology are used in the chips. So alerts that you will be getting, or the biometric you will be getting, that would be an integrated chip system. As we already have those biometric chips in the market, it would help us recognize through the biometric. Once the visitor visits the gate of the organization, there would be a biometric recognition using the sensor. So those chips are related to the semiconductor technology.
So I think you are registering using face recognition because booking your visit and all. So how you will be able to, take the biometric inputs?
Ma'am, as soon as you visit this application, you register yourself, there will be a face recognition. You need to recognize, you need to recheck if the same person is registering or not. Second, when you visit, there would be again a biometric with the help of the securities application, the same application, but by the profile of security. So they would then also recognize, they would then also register and match it with a background database that is pre-registered.
Shreya, we have already it in Amity, isn't it?
Yes, ma'am, we are using it in our amity. But are we using it for the guests? Are we using it for the parents that are coming up daily basis?
Okay.
Because as far as I know right now, if my parent wants to visit the campus, they need some approval from the PL. And it doesn't locate you, it doesn't show the GPS location.
Okay. Okay, thank you.
Ma'am, that
Thank
was
you, ma'am.
PC 18. That was PC 18. You can please record it. PC 18. And that was, dear participant, I request you to adhere to the timing and conclude it, be brief and precise. Okay. So next is PC 17. That was PC 18. 17. Again, Shreya Gupta, Amity University of Nanotechnology, carbon nanotube / PDMS nanocomposite bit strain sensor. PC 7. Yes, coming. Please share your poster. PC 17. Carbon nanotube based nanocomposite based strain sensor. Shreya Gupta, please share your poster.
Ma'am, she has mentioned. Shreya Gupta, are you there?
Anyway.
Let's move to the another participant, Mr. Nitin from Anna University. Mr.
Yeah,
Nitin,
hello. Yeah, hello, good afternoon.
are you there?
Yeah, I'm
Share
there,
your
I'm there.
poster. Please share your poster in
Your
full screen mode.
Your
Just give me a
poster
second.
topic is reduction of breast tumor effect using graphene-based terahertz antenna. Please share your poster.
PC 19.
Is my screen visible on the?
Yeah, your screen is visible.
Okay. So, yeah, first I want to thank Amity University for giving this opportunity for us to present our paper. Yep. So our paper, okay, I think something is not visible. Okay, my topic. Sure. So the topic we have did our project on is reduction of breast tumor effects using terahertz antenna. So the basic thing we wanted to do is just to detect if there is breast tumor in the breast. So here we have used CST software where we created a simulation of a breast and two antennas where we have one transmitting antenna and one receiving antenna. So by keeping two antennas, we create a two-port system so we can analyze with the S parameter values. So let me show you the design of my antenna. So the middle layer is the one where it is breast tissue, where it will contain three layers. First layer will be skin, second layer will be fat, third layer will be fibrogranular layer. So each layer will have different permittivity values. And the right hand side antenna will be transmitter antenna, and the left hand side antenna will be receiving antenna. Here we have used graphene as our material. So, and the antenna which we have used is micropatch antenna. So in the middle, you can see a spherical shaped figure, which is nothing but a tumor. So here in our paper, we have tried to do different type of thing. Like for example, there is one case study which we saw where there will be one layer called as melanoma layer. So it is developed due to the presence of tumor in some women. So we have added that layer and took the result. I've shown it here in the red color layer, and at the end is called as the melanoma layer. And sometimes, due to the presence of tumor, water molecules used to split inside the breast cells, and they used to form separate small spherical shapes. So due to this, also there might be something like we can detect if we have tumor or not. So I have also shown this figure here where we have simulated using this also water molecules. So the basic concept is that transmitting antenna will transmit electromagnetic waves due to the presence of different permittivity layers and different tangent losses. we will calculate S11, the power which is reflected back, and we will see if there is any change in the frequency. If there is any deviation in the frequency, then we can say that there is some abnormality present. And according to the change in frequency, you can say if it's a tumor, or and further cases, we can say that if it's a benign or a malignant tumor. So here, this is a setup. So in CST, we go and run it using some methods. And after we run, we'll get a graph, and we'll analyze the graph. And here I put a tabular column of different various conditions we run. So without tumor, the frequency was 1.79 terahertz, and with tumor, the frequency was 1.8 terahertz. So we can see that there's a slight difference of 0.01 terahertz frequency. So in normal cases, there shouldn't be any shift in the frequency, but we can observe there's a shift in the frequency. So we can say that there is some abnormality present. So if we want to further investigate on the issue, we can take S21, where we can see the energy loss. So if the energy loss is more, we mostly one of the most recurring cases in the human breast tissue is mostly it will be tumor. So for if there is going to be a shift in the frequency, we can.
Mr. Nitin, last 1 minute.
Please conclude.
Yeah, okay. So we can say that there is a presence of breast tissue. So the conclusion is nothing but we have created an antenna where we can detect breast tumor in terahertz frequency. There are lots of advantages in terahertz, and we are using graphene, which has lots of flexibility and which is very efficient. So I hope that if this product is going to be developed in the future, it will be more and more faster and reliable than what we are using currently we are using now, like CTs and MRI.
Okay, thank you. Ma'am, please.
Yes, PC19, can you hear me?
Yeah.
Okay. So you have all done all this through the simulation work. Was the setup also being done in the CST software?
Yeah, everything was done in the CST software, because to get breast tissue and simulate in the real time, so
Yes.
it requires a lots of permissions and requirements. So after this paper is like it has to go to many process if we have to do it in real time.
Okay. And the second thing is that terahertz is a huge frequency. It will, what effects it will have on in the human body and all?
So as per as we talk with many scientists, so many people are telling that terahertz doesn't have a very big effect on human tissue. So we might not have very big side effects when
Studies are
compared to
there already or not?
What?
Studies are there already on the
Studies are there
effect of
related to this.
terahertz on
Studies are there relating to terahertz, which is saying that it is very less harmful than what we are using now in megahertz. Right now, CTs and MRIs are in megahertz, so they have many side effects. Whereas when you go to terahertz, there are studies which show that terahertz doesn't affect our human body tissue.
Okay, thank you.
Yeah, thank you.
Next, PC20, Dr. Apara Tripathi from Gorakhpur University. Are you there, ma'am? Dr. Apara Tripathi from Gorakhpur University. Are you there? Dr. Tripathi? Mr. Rabin from Advanced Institute of Technology.
Sir, yes, sir. I'm there.
Yeah. Mr. Rabin, please share your slide. That is, ma'am, that is PC21.
PC20.
Please share a slide in a full screen mode.
Please conclude.
Is it visible? Is it visible, sir?
Yeah, it's visible.
Please conclude in 4 minutes. Okay.
Okay, sir. Okay, sir. Good afternoon, everyone. I'm Rabin. I'm here from the Department of Electronics Engineering from MIT campus. And here I'm to represent my co-authors for the work titled A Cross Dipole Wideband Antenna for Base Station Application. So we all know that now talking about wireless scenario, the role played by antennas is actually indispensable. So for the purpose of upholding the reliability in the service rendered, it becomes quite mandate that each and every individual parameters of antenna has to be looked at. Only then the reliable link can be preserved. So the major motivating factor for working on design of antenna for base station application is actually has been listed in two significant points. Point number one is that we preferably noticed only handful of literatures who have worked on antennas, especially when it comes to base station application. So, and preferably noticing those handful of literatures also, we preferably have observed shortcomings in terms of complexity or else in terms of size or cost, or else sometimes we have observed some level of compromise has even been established in terms of performance metrics too. And the second motivating factor for this research is that in wireless scenario, and especially when it comes to fast growing environment, LOS is actually not guaranteed between transmitter and receiver. So, with the intention of preserving the polarization purity of the transmitted signal so that the some level of signal integrity or signal quality can be preserved. Some level of measure is actually expected from the antenna engineers from RF front end, so that the signal which takes its propagation its integrity. So at the level of antenna designs, they thought in coming some called as polarization insensitive antenna, or else other named so as polarization diversity antennas. And another feature observed when it comes to polarization diversity antenna is that it serves even with feature called as frequency reuse concept, so forth, which is expected when it comes to preserving the spectral efficiency, especially when it to be criteria method anyone start or even for any application. So next is going to be the frequency. No, it is going to be the dictating factor of specific application, and apart from that, it is going to dictate the size of the antenna, which where an individual is going to end up with. And second thing is going to be the mounting location. It gives idea regarding the broader application area of usage of antenna design, whether it is for base station or else for mobile unit. And our intention is to work with antenna for base station application, seem to be a space intensive application. And point number 3 is directionality. So prevalently observing generation from fourth generation till at the beginning of fifth generation, we have observed that researchers concentrated more on usage of direct with the intention of preserving the scarce resource, this the spectrum, and also in order to preserve the power efficiency. And point number 4 is that in terms of polarization, as I already said, for the purpose of having polarization purity or else for the purpose of upholding the signal quality, it becomes a mandate to come up with something called as polarization insensitive antenna. So where we have concentrated on imbibing multiple polarization feature to the antenna, what we have designed
last
through
1
this.
minute, please be conclude.
Yes, sir. So through this research, I am about to conclude that this schematic gives an idea like even though base station being a space intensive application, we can observe that the antenna seems to be very bulky, and at the same the
Madam, you can directly come to your work without going.
Yes, ma'am.
Time is short.
So this is actually so occupy patient no dipole one over the other in cross pattern. So although this crossed dipole is radiator base station what we have planned for, and comparing this structure with the with this existing schematic, our structure seems very simple, and in terms of performance also, especially when it comes to port isolation also, we have outperformed, and in terms of size also we have reduced. So with this, I come to the conclusion of the say that even though base station being space intensive application, usage of our technology for designing antennas, it is actually a smart move for coming up with something called as cost conscious antennas and with no compromise on performance also. Thank you.
Thank you. Ma'am,
Uh,
please.
Poster 21, have you actually fabricated your antenna?
Yes, ma'am. We have fabricated and we were able to match our simulation and fabrication to utmost in closer level.
Okay. Thank you.
Thank you so much,
Next,
ma'am.
next PC 22.
Rabi Khan from Amit Institute of Nanotechnology.
Yes, sir.
Please share your presentation. Please stick to your work and conclusion. What results you have got, okay?
Is it visible, sir?
Yes, visible.
Yes, visible.
Okay, sir. First of all, a warm good afternoon to everyone. Myself, Mohammad Ragib Khan, student of MSc Integrated MTech Nanotechnology, MIT University, Noida. I would like to thank the organizing committee for giving me a chance to represent my presentation on the topic non-enzymatic dopamine detection using an electrochemical sensor based on 2D graphene nanocomposite. So, for a brief, a short introduction, dopamine is a catecholine neurotransmitter which is produced in a dopaminergic neurons, and it plays a very critical role in motor activities, reward, motivation, and cognition. If we talk about in a layman terms, we say when we get happy, dopamine level in our body increases, and when we get sad, the dopamine level decrease as per the our mood. So abnormal dopamine level leads to a shortage, like the shortage of dopamine or loss of dopaminergic neuron leads to several neurological disease, which could be Parkinson disease, drug dependency, schizophrenia, and ADHD. If we go for the traditional methods which were present for detecting the dopamine, could be HPLC, chemiluminescence spectroscopy, electrochemical detection. These all methods were present earlier, but they have some disadvantage, which was that they take very time for detection of the dopamine. For that, we came up with a new technique like electrochemical technique, which include voltammeric analysis, which offers us high specificity, sensitivity, and ability to perform on-site test without preconditioning. Then we have came with a material like a carbon. Carbon has a carbon nanomaterials in which we have basically focused on the graphene because of its electrochemical sensor use, because of their electrical activity, conductivity, chemical stability, biocompatibility, and large surface area. So we have taken a composite of graphene with iron salvinohydride, which shows us super sensitivity, selectivity towards dopamine. If we talk about I talk about the synthesis of the graphene. So we have used electrochemical setup in which we give a two electrode system. One is graphite as a cathode and anode for the platinum rod. Then we have exploited graphene. We have performing washing for the removal of ionic species. Then we have performed probe sonication, centrifuge, and we have separated the graphene in two different containers for checking the.
Presenting a specific research get
If we
certificates.
go for the characterization, we have for now I have two characterization results. One is for XRD and the FESM. In which FESM we have microscopy is around 5 micrometer, and for XRD we got a plane at 001, which shows the presence of graphene in our sample. If we talk about the result part, I have done CV for the result and amperometry. In CV, I have compared three different GCE. One is for bare GCE, the other one is graphene GCE, and the third one is our composite. So the
Please
green color
conclude.
peak is showing graphene composite, which shows the current peak is more. For the second 3B figure, we have done different concentration and we got the peak around 0.2, which shows the dopamine peak detected by our composite. Further moving with the different scan, Different scan rate shows the adsorption and desorption of the dopamine on the surface of the composite. It shows the linearity, and the further moving with the amperometry, it shows the linearity of the linear concentration detected by the dopamine. So from this, we have concluded till now that the selected composite is effective in detecting dopamine and demonstrated stability and selectivity. Further, the combination has potential to function as an electrochemical sensor for detecting dopamine. And from this, we have concluded that further study is required for the confirmation of composition, and we have to check with the different.
Is concluded.
Yes, sir. And from this, we have concluded like we need further more analysis.
The student name Nitin representing research. As,
Thank you, Ravi.
Poster 22, is it complete? Your presentation is done?
Yes, ma'am.
Okay. So I have one question. Have you done any sensitivity studies on this?
But this is an ongoing case. So until now, I have done CV, amperometry, and EIS.
Okay.
And for the synthetically produced dopamine, like synthetically produced dopamine.
Okay. Okay. Thank you. Thank you.
Next.
Others, please mute your mic.
Thank you, ma'am.
Next.
Mr. Vijay Bhatt from Department of Physics,
Yes, sir.
University of Delhi. Please share your slides.
Yes, sir.
PC 23. Because this is a poster session, we cannot give you more than 5 minutes. So please stick to the timing. Okay. Please conclude in under 5 minutes.
Good afternoon, everyone. My topic of presentation is enhanced bistable switching characteristic in hybrid optomechanical system with quantum dots in modulated fields. And as you can see that it is a theoretical model that is the cavity is made up of the two DBR mirrors that you can see that the two modes are formed in between cavity mode A and cavity mode B, and the coupling is between these two modes, and the quantum dot is placed in the cavity mode B. The one mirror is perfectly 100% reflecting, and another mirror is partially reflecting mirror, and this mirror is movable mirror also, so making it optomechanical system. So we can write the Hamiltonian for this system that is written here, and these are all the parts of these energies that it contains of various modes, both the modes and coupling between these two, and this is the harmonic oscillator energy. So after doing the theoretical calculations, we got these results. In the steady state, we got these by these hysteresis type loop curves that are known as bistability. So we can see that by varying the parameters, like this is
Other participant, please mute yourself.
by varying the cavity detuning, that we can see that the as we are changing the cavity detuning, the bistability curves is going towards the lower input power. So this bistability is leading to the behaving like a optical switching like behavior, because this is the this lower part is showing the off state, and this higher output power is showing the on state. So we can see that by optimizing the various parameters, we can go for lower power consumption switches. This leads to and by varying the various optimizing these like the optomechanical coupling, and this coupling between quantum dot and the second cavity mode, and by this detuning quantum dot detuning, we can vary the we can vary the optical bistability curve, and we get the cost effective optical switching behavior. Thank you.
Well, very good.
Hello, Vijay ji, I have one question. What
Yes,
are
ma'am.
the important findings in this research?
Important findings are that this as you can see in the graph, that the this is going like it is between the input power and output power. So for lower input power, we are getting the switching like behavior. So this leads to the low power consumption. Our main motive is to build optical switches that are cost effective, and they work on lower power regime, that can go for lower power regime. And these parameters, when we varying these parameters, that are going for lower power regimes.
Okay, any studies on switching speed?
Switching speed, yes. By these plots are used for like gain and switching ratio, can be used for gain and switching ratio, and another studies for this. Based on these graphs, we can calculate the switching ratio and gain also for the optical switches.
Okay, you seem to be doing a DST project, but the
Yes.
references I see, they are 40 years back. So kindly adhere to what the latest research that is happening, 84, 85, you see. So about
Yes.
40 years back references.
These are basic of this study. So I have not like this is a emerging field, and lots of studies are going on based
yeah.
on this. That's why I have put it
Just for
these.
comparison purpose, you need to use some latest references, and also you try to mention those as well.
Yes, ma'am. Yes, sure. Yes.
Thank you. Thank you.
Thank you, ma'am. Thank you
So
very
next speaker, PC24,
Miss
Sonia Yogi.
Sonia Yogi from Amity Institute of Advanced Research and Studies.
Okay, I'm sharing this.
Please adhere to the timings.
Oh,
Please share your presentation in full screen mode.
is my screen visible?
Not yet.
Up till not.
Chomli, can you please share my screen? My poster by your laptop. Hello?
Okay, yeah, sure. I'll do that.
No, your screen. Yes.
My screen is visible?
Yeah, kindly make it a full screen mode.
I think you are
Is it
using.
visible?
Yes, yes.
Okay.
You'll have to scroll it.
Chomli, please do. यहाँ से नहीं होगा.
Yeah, it's visible.
Good afternoon, everyone. My name is Sonia Yogi. I'm a PhD scholar in MT Institute of Advanced Research and Studies. I'm working under the supervision of Dr. Avashish Kumar in Material and Device Department, MIT University, Noida. My today's topic of poster presentation is highly sensitive and selective RGO-CO nanocomposite based CO gas sensor. So in this poster, I'm discussing about the sensing of the carbon monoxide using the RGO sheets. We are making the composite of RGO, that is reduced graphene oxide and copper oxide. Reduced graphene oxide was synthesized by the using modified Hammer's method, and copper oxide nanoparticles were prepared by the chemical method. The prepared device was then rigorously tested for the carbon monoxide gas through the various concentrations starting from 0.5 ppm to the 100 ppm, and we have seen that the sensor response is more than 38% for the 0.5 ppm with the fast response and recovery time. Response time was 1.5 seconds, and the recovery time was found to be 4.5 seconds. So one more parameter of the sensor is the stability. So we have seen that the device is stable for the 30 days, and it was also selective for the carbon monoxide gas. these are in the result and discussion section, you can see that these are the characterization graphs of the first graph is the micrograph of the reduced graphene oxide, and second is the SEM micrograph of the reduced prepared composite, that is of reduced graphene oxide and copper oxide. This is the EDX of the prepared sample, and the graph figure 2B is the mapping of the various elements present in the prepared nanocomposite. In the result section, first graph is the graph between response and time, and we can see that the response time is here 1.5 seconds and recovery time is 4.5 seconds. Second graph here, which is between resistance and time, shows that the repeatability of my prepared sensor for the 4 cycle. Third graph 3 is the shows the selectivity of the sensor. We can see that the response of the for the carbon monoxide is higher than higher with respect to the other gases like ammonia, sulfur dioxide, and methane. Fourth graph is the response versus number of day, that is, it shows the stability. So our sensor, in conclusion, I can say that the sensor is highly responsive. It is 1.5 seconds. Recovery time is also 4.5 seconds.
Please be concluded.
I'm concluding it. And the response is 38%, greater than 38%, and it is at the 0.5 ppm, that is at very low concentration, and so it is stable and selective. That's all. I wish to express our gratitude to the founder president of MIT University, Dr. Ashok K. Chauhan, for this encouragement and guidance, and all the staff of the MIT Institute for the Advanced Research and Study Material and Devices for their support. Thank you.
Thank you, Sonia. Ma'am.
Sonia, where you have developed this sensor?
Ma'am, in our lab, Material and Devices, in MIT University, Noida.
Okay, you have done. And where you have done the testing?
In the Noida itself, in the same department, sir, ma'am.
Okay.
I'd like to ask a question, if the moderator allows me.
Yes, please.
Sonia, your PPT is not clearly visible to me. I'd like to ask you about the retrieval of your sensor. The graph in which you have shown the response and the recovery time. I'm not sure whether it has retrieved back to the 90%.
Sir,
if you can see the plot below your EDX plot.
This one, figure A, sir, figure 3A.
I think, yes, figure 3A. I'm talking about figure 3A.
4.5 seconds, are you talking about? Sir, it is approximate 4.5 seconds because we are also working on that part so that it will become 90%. This 90% of the initial value of
what
the
I mean to
resistance.
say is the retrieval is it's still not 90%. Am I right? Yes,
So,
this one.
Sir, we want to just yes, it is approximate 90%, sir, 89, 85.
Okay. Yes,
Okay.
now it is clearly visible.
So, sir, have you done?
Thank you.
Thank you, Sonia.
Next speaker is
Gunjan Mishra.
Gunjan Mishra, Department of Computer Science Engineering, Babu Banarasi Das University, Lucknow. PC 25. Are you there? Hello, Gunjan, are you there?
Gunjan Mishra.
Next. Go to next one.
Dr. Arif from Department of Chemistry, Aligarh Mission University. Dr. Arifa, sorry. Dr. Arifa, are you there? Dr. Arifa?
No, next.
Alina? Miss Alina?
Hello, yes, I'm here.
Share your poster.
Yes, sir.
Conclude within 5 minutes, okay?
Yes, sir. I'll conclude my presentation within 5 minutes only. Okay, sir.
Ma'am, PC 27.
Is my screen visible?
Not yet.
Uh, is it visible now?
Yeah, it's visible.
Please
Make it full screen mode.
Okay, is it visible?
Please continue.
And I'm audible now? Okay.
Yes.
Okay, I'll conclude it in 5 minutes. Okay, thank you. Good afternoon, everyone. I'm Alina Kulsum Abbasi from Amity Institute of Advanced Research and Studies, Materials and Devices. I'm working under Dr. Rakhi Grover. And I'm delighted to present a poster on my work based on silicon nanowire perovskite heterojunction-based photodetector. This work reports all solution-based photodetector fabricated by using silicon and silicon nanowire heterojunction with perovskite. The perovskite material used in this work is methylammonium lead bromide, which has the characteristic crystal structure with formula ABX3. In the figure, you can see A site cation methylammonium is located at the center of the lattice. B site cation, that is lead, located on the corners of the lattice. The ideal cubic structure has B site cation in 6-fold coordination surrounded by an octahedron of bromide anions, and A site cation is in 12-fold cube-octahedron coordination. The band gap of methylammonium lead bromide is reported to be 2.3 electron volt. This band gap can be further tuned by substituting the A, B, or X site cations or anions. Perovskite materials are increasingly being used as photodetectors due to their exceptional light absorption properties and a high sensitivity to a wide range of wavelengths. Photodetector is an optoelectronic device that converts incident light such as electromagnetic radiation in UV, visible, and infrared spectral regions into electrical signals. The aim of this study is to fabricate silicon nanowire perovskite heterojunction-based photodetector, leveraging the unique advantages of both the materials to create a highly responsive and fast switching optoelectronic device and to compare the performance of silicon nanowire with silicon as substrate. Unique properties that make silicon nanowire a desirable substrate is its quasi one-dimensional electronic structure, high sensitivity, and high surface to volume ratio that allows better coverage of material on its surface. The figure on top right, you can see it shows an illustration of silicon nanowire along with methylammonium lead bromide crystals coated on top, and the device structure with silver as counter electrode and material for making contact. The photodetector was fabricated using one-step spin coating technique to deposit the perovskite thin film on silicon nanowire and silicon wafers. Perovskite solution was made by mixing methylammonium bromide and lead 2-bromide in dimethyl formamide and dimethyl sulfoxide. And silicon nanowire was fabricated using metal-assisted chemical etching technique. So the perovskite solution, substrates were cleaned using dilute hydrofluoric acid, deionized water, and ethanol subsequently, and then dried to remove the oxidized silicon layer from silicon wafer exposed to the atmosphere to get a uniform pinhole-free thin film of perovskite. And then polished surface is used as electrode, and perovskite is coated on the edge surface using spin coating technique. Then conductive silver paste was deposited, drop casted for making electrode contacts, and the device is ready for testing. So the results are here in the graph. You can see the optimized heterojunction of silicon perovskite, the film. It exhibited spectral responsivity of 64.5 milliampere per watt as it was calculated. Whereas that of silicon nanowire perovskite device, it exhibited spectral responsivity of 51.2 milliampere per watt under white light illumination. The time domain response of the photodetector showed a fast photo switching response with rise and fall time in the range of 0.5 seconds for silicon perovskite device, and it was faster for silicon nanowire perovskite device. It was 0.3 seconds. The temporal curve you can see of silicon perovskite device, it shows declining photocurrent, whereas in case of silicon nanowire perovskite device, photocurrent remains stable and exhibits comparatively faster photo switching response. The methylammonium lead bromide film It exhibited green emission under UV lamp, which can be seen in the picture. That perovskite was originally under normal light, it was yellow, orangish yellow, but under UV lamp, it was green. Photoluminescent emission peak was centered in 535 nanometer. UV visible absorption band of methylammonium lead bromide was showing
Miss,
a significant
please
peak.
conclude.
Yes, sir, within a minute. It showed a significant peak at 528 nanometers. Therefore, a successful fabrication and characterization of high-performance silicon and silicon nanowire perovskite heterojunction-based photodetector was demonstrated. And the detailed investigation of perovskite material properties and the optimization of device structure provide valuable insights for further development and commercialization of these innovative photodetectors. That aligns with the title of the conference, Materials to Chips. That's all. Thank you very much.
Thank you.
Thank you. Any questions?
PC 28, Shamili Roy.
Thank you, Alina.
Thank you very much, sir.
PC 28, Shamili Roy from
Yes,
MIT
sir.
Institute of Advanced Research and Studies. Please share a presentation.
Sir, I'm not able to share my screen actually. It shows, can you share?
Now you can share your presentation.
Yes, sir. So 1 second, I'm just. So is it visible now?
Not yet. Yeah, it's visible. Please make it full screen mode.
Okay, sir. Sorry, sir. So I have done it in slideshow mode. Is it visible
Please
in
please
slideshow
continue.
mode?
Yeah, please continue.
Good afternoon, everyone. I am Somli Roy, and my topic for today's poster presentation is high performance and ultra sensitive humidity sensor based on polypyrrole, which is PPY, reduced graphene oxide, a nanocomposite on silicon substrate hybrid nanostructure. In this work, we have developed a high performance and cost effective humidity sensor using a PPY RGO nanocomposite on silicon substrate. This sensor has exhibited excellent sensing characteristics of up to 85% change was measured in resistance in the range of 50 to 80% relative humidity. So relative humidity is the ratio of water vapors present in the air with it is the ratio of water vapors present in the air to the maximum possible vapors which can be contained in the air at that temperature. Humidity sensor measures this relative humidity. This relative humidity measurement is very crucial for different industries like healthcare industries. It is extremely important. Agricultural planting, like meteorological monitoring and everything. It's extremely important in these industries. So for this, in this work, we have developed the RGO using the modified Hummer's method. PPY, which is the polypyrrole, was developed by polymerization, and the composite was prepared by sonification of these two powders. The solution that we got with this solution, the connections that were made were with on the sensor were by soldering wires and on a PCB. Silver paste, we use silver paste to establish the contacts on the sensor. We used electrometer, as you can see here in this schematic diagram. We have the setup of testing space where we have tested the sensor for humidity in relative to produce a humid environment. We have this enclosed space. We have used glycerol and water to produce the humidity in the environment. The readings were measured with the Keithley electrometer, and we have collected the data on the data acquisition system. So in our findings, we have found that the current, as you can see in the first graph, figure 2, that it for the RGO PPY on the silicon substrate only, we have got excellent sensing results, and the current was also it was higher than, if you compare it to figure 3, it was higher than in when you do it on a ITO substrate. In figure 4, we have shown that the response time at 60% humidity was around 8 seconds to, and the recovery time was a little higher. Response time was around 12 seconds, 8 to 12 seconds, and recovery time was around 30 seconds, which was a little bit higher. But you can see in the voltage measurements as well that RGO PPY compared to ITO, it shows a relatively stable response. And the SEM image of our PPY RGO composite shows that the nano composite that we have prepared ultimately has been successful, and this is the SEM image for that. So in conclusion, I would like to conclude that
Please conclude.
by developing, we have successfully, yes, sir. So we have successfully developed this humidity sensor, which can be used in various applications in various industries. The efficiency of the sensor is, the sensitivity of the sensor is 85%. It was measured. Humidity sensor was the one that was based on the SI substrate, shows much higher response than the ITO substrate. And I would like to acknowledge Amity University for giving me this opportunity to present the poster, as well as for letting me work on this topic. Thank you, sir.
Ma'am, can I ask one question? Shomli,
Yes, sir.
have you done any temperature effect study on this sensor, or is there any study?
No, sir. Every study, no, sir. Studies, every study that was done was on at room temperature, because so basically the commercial humidity sensors that we have, they work at very high temperatures. So our goal was to produce a sensor so that a sensor that works at room temperature, which is very important for commercial purposes, room temperature sensor.
Yes, but temperature studies are necessary for that. You can do that. Okay. Anyway, thank you.
Next participant, Dr. Fozia, Department of Physics, Maulana Azad National Institute of Technology from Bhopal. Dr. Fozia.
Good afternoon, everyone. Can you hear me?
Yeah, we can hear you. Please share your slides.
Yes, yes. I'm Dr. Abhinav Bhargav, presenting on behalf of Dr. Fozia Haq, and I'm sharing my slide. If it is visible, please let me know.
Okay.
Okay, just a minute. Okay, is it visible as full screen?
Not yet.
Wait.
Okay, just check me one. Let me check once again.
It is visible now.
Okay, okay.
Camera is
Is it visible as full screen now?
Yeah, it's visible. Please continue.
Okay, so today I'm going to present a study on chemoresistive sensor, and here we are going to sense the ammonia gas with the help of WO3 material, which is known as tungsten oxide. And we are doping SN, that is tin, inside this tungsten oxide material to increase its efficiency. So chemoresistive sensors are those sensors basically which works on the variation in the resistance. Why we have taken tin as a material to indulge itself in the WO3 matrix? Because tin is an important metal and it contributes a lot in terms of electrons when we talk about the band gap energies and other communication in electrical transport. This material WO3 we have prepared with the help of co-precipitation method, and through XRD we have confirmed that we have a polycrystalline nature. We can see in the XRD that we have obtained a clear structure of polycrystalline nature, single phase with doping wise concentration also. We have doped tin in percentage of 0.5, 1, 1.5 and 2.0. To confirm the nano crystalline structure of these samples, we have done FESEM along with EDX to confirm whether what amount of material or the elements are present in our compound. FESEM images shows us that the structure are well-defined nanostructures as well as a little bit type of distorted rod structures. In this, we have also confirmed the XRD with the help of JCPDS file 20-1324. All samples show orthorhombic structure in their nature. Going ahead, we have performed UV-VIS spectroscopy to confirm the band gap of all the compounds, the undoped and the doped systems. We have seen that with the doping of SN in the interstitial sites of tungsten oxide, the band gap reduces. However, it is encountered that the most optimized system we obtained at 1% doping of tin, which will be confirmed further in other responses also. To check whether in which region the absorption is taking on, and to confirm that, we have done a photoluminescence spectroscopy. Photoluminescence spectroscopy show that all the samples exhibit their response in visible spectrum, and a major shifts are obtained, and they are shown in the wavelength range which are observed on the screen. To further conclude our work, we have used the gas detection, sensing response, and sensitivity graphs. In that, we have used ammonia gas. We have inserted the ammonia gas. We have extracted the ammonia gas. When we are inserting the ammonia gas, we observe the change in temperature, and that are shown in the graphs. As we have seen, the most optimized system we have encountered after doing all the stuff, that is the 1% SN. We can say that when we start the amalgamation of any further element into a foreign or exotic material, we see that at certain percentage it get optimized. So after observing all the details, we have encountered that at 1% of tin, we have optimized material, which is behaving so well that we are getting a very good response. We have also plotted the sensitivity versus doping concentration graph, and in that we can see that maximum sensitivity is obtained at 1%. We have concluded that after encountering the ammonia gas at 200 ppm, that material doped with 1% tin has shown a response of 96.98%. And in this way, we can say that WO3 nanostructures demonstrate considerably higher response than conventional hydrogen sulfide and alcohol-based sensors. I want to acknowledge Merit Director Bhopal, who have contributed towards providing us facility to perform all these experiments, and I am thankful for other authors for their contribution. Thank you.
Thank you.
Abhinav, have you compared your sensor with the others which exist for this?
Yes, ma'am, I have quoted them in the literature and cited as well. The previously mentioned samples or previously mentioned sensors are taking a lot of much time to respond. We have recorded
how much difference is
10 seconds and 14 seconds.
How much
there were nearly 40
in your
seconds.
response and theirs? Yes.
Their response time was 40 seconds nearly, and the concentration they needed was quite high. As compared to that, we have a response time of between 10 to 14 seconds, and that concentration of low percentage is also detected in our sensors.
Okay, thank you.
Thank you. Next, PC30, again, Dr. Fozia, who is going to present it? PC30, fabrication of FLA wide dope manganese dioxide.
Hello.
PC30. Yeah, please share your presentation. PC30.
Good afternoon.
Please share your
Good
presentation.
afternoon, sir. Am I audible?
Yes, you are audible. Please share a slide.
Is it visible, sir?
Yeah. Kindly make it full screen mode.
Yeah, please present.
Okay. Good afternoon, everyone. First of all, I would like to thank ICST committee members for giving me this opportunity to present our work titled Fabrication of Leavenite Doped Manganese Dioxide Polyvinyl Alcohol Nanocomposite Film for UV Shielding. As we all know, ultraviolet radiations are very harmful. It can manifest long and short-term health issues like aging, sunburn, skin cancer, etc. In this context, increasing concerns over human health and environmental protection have generated great interest in the UV shielding materials. There are basically two types of UV absorber, organic one and inorganic ones. Organic ones are avobenzene, oxybenzone, etc. And the inorganic ones are TiO2, zidino, cerium oxide. These absorbers are used in various screens of mobile phones. Inorganic absorbers such as TiO2, zidino have been primarily considered for UV shielding, but only below 320 nanometers due to its inherent wide band gaps. I have used manganese dioxide. It is an N-type semiconductor with UV radiation strongly up to 400 nanometers. To deal with the side effects of UV light exposure, polymer nanocomposite will be the best option. This polymer nanocomposite is in which nano UV absorbers will absorb the UV, and the polymer part will be used as coating over anything like glasses, or it can be used in sunscreens. The reason to choose polymer as the base material is because it is cheap, it is intoxic, transparent, and flexible as well. Hence, our main objective is to develop a polymer nanocomposite which can shield from UV and let visible light to pass through it. In this work, we have reported the preparation and characterization of flavonoid doped PVA manganese oxide nanocomposite film. In typical synthesis, we have measured 1.5 milligram of potassium permanganate and prepared a solution of potassium permanganate in 10 ml deionized water with continuous stirring for 30 minutes. After that, we have prepared a solution of sodium thiosulfide in 10 ml of deionized water, and then the solution of potassium permanganate was added in sodium thiosulfide with continuous stirring. With this, we can incorporate the changes. The color of the solution will change from purple to yellowish brown and finally appear to be dark brown. This dark brown color confirms the formation of manganese of flavonoid doped PVA manganese dioxide nanocomposite is as follows. We have taken 2 weight percent PVA solution was prepared in deionized water, and 1 weight percent and 2 weight percent manganese dioxide solution was added dropwise with continuous stirring at 80 degrees centigrade. After that, we have added 0.1 weight percent amount of flavonoid. After 15 to 20 minutes of stirring, a solution was duly spread in petri dish and kept in oven at 50 degrees centigrade for 24 hours and finally peeled off carefully for characterization. We have done the UV absorbance spectroscopy of these samples. As you can see, pure PVA is somewhat showing the absorbance in UV range, and 1 weight percent is showing up to 0.8 absorbance, and 2 weight percent is showing more absorbance than the 1 weight percent. And we have the transmittance graphs of these samples. PVA1 is showing up to 80% transmittance. The transmittance of 1 weight percent is up to 70%.
Please conclude.
And the transmittance of 2 weight percent is up to yeah. So we can conclude that from this, my 2 weight percent sample is good for UV shielding property because it is showing more absorbance in UV region. Okay, thank you.
Have you tested your sensor? PC poster 30. Have you tested your sensor for UV absorption and all?
Yeah, ma'am, I have already shown the graphs of UV absorbance. This is for UV shielding, ma'am, UV shielding property.
Okay.
Ma'am is asking, have you tested
thank
this
you.
sensor in on field? Anyway, what is the absorption range? It is not clear.
Sorry, sir.
Till what wave?
Absorption range is.
It will absorb the light. Whether it will work on UVC or UVB.
Sir, as far as work on UV and UVB.
Okay, anyway.
Mr. Akash Kumar Gaur. Mr. Akash Kumar Gaur from Amity Institute of Nanotechnology. Are you there?
Please unshare your presentation. Yes.
Mr. Akash Kumar Gaur.
Okay.
Mr. Imtiaz Hussain.
PC32, are you there?
Mr. Imtiaz Hussain from Department of Physics, St. Andrew College, Gorakhpur. Are you there? Mr. Imtiaz Hussain. Dr. Tripathi, Dr. Apara Tripathi from Department of Physics, Gorakhpur University. Are you there? Dr. Apara Tripathi from Department of Physics, Gorakhpur University. Are you there? Okay. नहीं. Gunjan Mishra from Department of Computer Science and Engineering, Babu Banasi Das University, Lucknow. Are you there? Gunjan Mishra from Department of Computer Science and Engineering, Babu Banasi Das University, Lucknow. Dr. Arifa from Department of Chemistry, Aligarh Muslim University. Are you there? Dr. Arifa from Department of Chemistry, Aligarh Muslim University. Last, Mr. Akash Kumar Gaur from Department Amity Institute of Nanotechnology. Are you there? Is anyone participant left for his or her presentation? This is the last call. Is anyone participant left for his or her presentation? Kindly share your screen.
Tell your poster number and title if you have left.
Hello.
Shweta.
No, sir, Pooja here. Poster number 33.
Hello, I am Dr. Shweta Chore. I was supposed to present on 18th.
Okay.
Hello, can you hear me?
Yes,
we can hear you. Please share your screen.
Yeah, thank you.
Can you tell me what is your poster number?
Just a minute.
Please share your presentation.
Yeah. PC5. My poster number was PC5.
Okay. Please share.
Is it visible?
Yeah,
Yes.
it's visible. Kindly make it full screen mode.
Okay.
And please stick to the timing. We have only 5 minutes.
Yeah.
Thank you.
Yes, sir. Okay. Actually, I'm Dr. Shweta Chore. The topic of presentation is refractive index control in nanocomposite atrazine films, nanocomposite PMMA atrazine films for atrazine detection. Atrazine is a herbicide. It's a man-made chemical and extremely harmful to wildlife and aquatic animals, as well as the endocrine it's a disturbing chemical interrupting regular hormone function. It causes birth defects and many more other defects in the human beings. It is very important to detect it as it is water soluble and it is an herbicide. It's very important to detect it. Okay. So we have fabricated a sensor or a sensing layer which can detect this atrazine in water. The system investigated over here is PMMA and MIP composite films. PMMA is a host material because it's optically transparent and and mechanically stable. Also, it does not react with molecular imprinted polymers and hence does not modify the structure and functionality of MIP molecules. Molecular imprinted polymers have the binding sites which specifically binds with the atrazine. They are specifically fabricated to bind with the atrazine molecules. The sensing and detection of atrazine is done by measuring the change in the refractive index of PMMA MIP thin films, and hence optimization of refractive index of sensing layers is very, very important. The composite layer is fabricated by spin coating, and spin speed, sonication time, relative concentration, all the parameters are optimized in order to achieve appropriate sensing layer. After optimization, it was found that the PMM and MIP with a ratio 2:1 is suitable to act as the sensing layer. Now, after formation, the PMMA MIP layer with the suitable concentration is mixed and is spin coated on the silicon surface. The AFM studies were done. PMMA has porous and uniform structure without any special features, and the composite film shows the granular morphology and does not reveal the porous structure. It shows the AFM micrograph clearly shows the significant change in morphology as compared to the only PMMA films. The spectroscopic ellipsometry measurements have been done, and it is observed that the spectra is measured in the range 350 nanometer to 800 nanometer, and delta and psi, the delta and psi parameters are recorded. Actually, ellipsometric technique analyzes the change in the polarization state when the beam of polarized light is reflected from the surface or interfaces of the coating. The psi measures the magnitude of reflectivity ratios of P and S polarized light, and delta measures the phase difference between P and S polarized light. So, the binding of atrazine molecules result in the change in the optical constants and thus the refractive index near the surface. The experimental values clearly shows the change in delta and psi values when the membrane is exposed to atrazine solution. Delta values changes from 86.9 degrees for membrane to 106.73 degrees and 111.91 degrees for membranes when they interact with 1 ppm to 100 ppm respectively. And delta and psi changes from 26.14 for membrane to 22.21 and 13.78 for 1 ppm and 100 ppm. So there is a significant changes in delta and psi curves in response to interaction of atrazine with composite sensing layer. The change in delta and psi values, they clearly show that the optical constants of PMMA MIP membrane are changing after interaction with analyte. The refractive index change has also been optimized and calculated by the softwares which were available and using the Cauchy's formula, and the substantial change in the delta psi values has been
Please
observed.
conclude.
Yeah, the results show the binding of atrazine molecules results in change in the optical constant and thus the refractive index near the surface, and hence this material can be used for atrazine detection in water. Thank you very much.
Thank you, ma'am.
Ma'am,
if you want.
Yes, Dr. Shweta.
Yeah.
What are the harmful effects of atrazine?
It's
In
a
our
full
human
effects of
beings?
atrazine. Yeah, it's very dangerous. Actually, it is used in agriculture as an herbicide, and easily dissolves in water, and it can go into the water bodies, and it's an endocrine disrupting chemical. If it is consumed in large amounts, it can cause the birth defects, reproductive tumors, and in humans also, and in amphibians as well.
Okay.
So it's very important that we should detect it in water bodies, because it can get consumed by humans.
Thank you.
Thank you very much, ma'am.
Thank you.
Thank you.
Next participant, Miss Pooja Singh. Are you there?
Yes, sir. Yes.
What is your poster number? PC 37 or 34?
So it is 36.
33.
34.
34.
Yes, sir.
Rajesh.
Miss Pooja, please share your slides.
Yes, yes. Yes, sir. Is my screen visible?
Just a moment, Pooja.
Yes, sir.
We will like to thank Professor Sujata Pandey ma'am for chairing this session. And because of her, we have gone our e-posters very well. And on behalf of organizing committee, we are thank you very much, ma'am. Ma'am, we request you for the lunch, please, ma'am. Thank you, ma'am. Yes, Pooja, you can continue now.
Okay, sir. Sir, my screen is visible.
Yeah, please continue.
Yeah. So the title of my poster presentation is the self-biased high-efficiency optical sensor prepared using heterojunction on silicon nanowires on silicon chip. I am Pooja Singh and I am pursuing PhD from MIT Institute of Advanced Research and Studies, MIT University, Noida. So as the optical sensing device, these are generally based on the heterojunction and they are getting more attention nowadays because they are showing promising application in various sectors. So this work is based on the near infrared range. So this range basically lies from 700 to 1400 nanometers. And this particular infrared sensors find wide application in military communication, medical and environmental monitoring, remote control, and thermal imaging and night surveillance. So generally, NIR sensor based on the third, fifth group of materials. And out of these, we have mercury-based alloys, that is HgCdTe. And these methods are generally expensive, complex, and hazardous to environments and to the living organisms. So besides this, we are working on the silicon nanowire so that this silicon nanowire can be integrated into our existing silicon industry. And in order to this, we develop a fast, simple, highly sensitive NIR sensor, which can be easily integrated into the existing industries. So here we synthesize silicon nanowires by using the metal-assisted chemical etching, and we procure TiO2 nanoparticle whose band gap is of the order of 3.2 electron volt, and we synthesize RGO whose band gap is from 1 to 1.69 electron volt. So this is the method which is showing the metal-assisted chemical etching. First of all, the silicon substrate is cleaned sequentially with DI water, acetone, and IPA for 15 minutes. And then it was immersed in the piranha solution for 30 minutes. And after that, we rinse it with the HF solution and dip it in the etching solution. And lastly, it was rinsed with HNO3 for 10 minutes. Whereas for the synthesis of RGO, we opt CVD method. So here the silicon substrate was cleaned ultrasonically and then copper as catalyst film was prepared on this substrate by using the RF sputtering system. The CU catalyst coated substrate was used for the growth of graphene. So before the start of the growth process, the system chamber was purged with inert gas in order to remove the contamination. And then the chamber of the system was evacuated to a pressure of approximately 60 mbar. For the growth of graphene, two steps were followed. Firstly, the substrate was preheated for 10 minutes at 50 degrees Celsius under the presence of nitrogen gas. And after the pre-treatment process, methane as a source gas was inserted into the CVD chamber. And during this process, the temperature of the substrate was rapidly increased to 650 degrees Celsius and the growth time was approximately 15 minutes.
Please be concluded.
Yes, so these are the characterization result, which is showing the SEM graph of the silicon nanowire. And this is the SEM micrograph of RGO TiO2 deposited on the silicon nanowire. So these are the EDX color mapping of the carbon, oxygen, silicon, and titanium, which are observed in the SEM images. And here I'm showing the UV response, UV absorption spectra of RGO TiO2, and it is recorded from 300 to 700, and the peak was observed at 340 nanometer. So this particular device is showing its repetitive nature for the 940 nanometer. So here we observed it for 5 on-off cycle. And we also observed the photovoltaic voltage across it, whose value was approximately 100 millivolt, and photocurrent was approximately 40 microampere. And this shows good reproducibility with good responsivity and detectivity. So here is the conclusion of my work. So this is basically a high performance IR detector, which was successfully demonstrated by developing a heterojunction between the RGO and TiO2 over the silicon nanowires. So as we already see the SEM images, it is showing a 2D layers of RGO, which is deposited over silicon substrate, and uniform deposition of RGO TiO2 over silicon nanowires. We observe a good photovoltage of 10 millivolt and a photocurrent 40 microampere under the photovoltaic condition. And we got a responsivity of 17.2 into 10 power minus 17.2 milliampere per watt, and detectivity is also very good, that is 0.23 into 10 raised to the power 11 joules. So the response time was less than 1 second and decay time was less than 3 seconds. So here we can say that it is a good photodetector which can use for the IR sensing application. So this is with the conclusion. So here are the references. And I would like to thank Dr. Ashok K. Chauhan, the founder, president of Amity University, and the faculty members of Amity Institute itself. Thank you so much.
Sir, please, any question?
Yeah, thank you, Pooja. Pooja, how can you justify that your sensor is for a whole IR region or far IR or near IR or?
Sir, it was for the near IR region only because we sense it for the 5 IR as well, but it was not showing any responsivity at that time. So it is particularly for the near IR range.
Okay, and how do you keep your sensor in front of the other existing sensors, commercially available sensors?
Sir, these sensors are based on the silicon nanowires and which show good integrity with the existing one. Others are basically based on the other material itself, so which cannot be easily
Have you
integrated.
checked any reproducibility or something?
Yes, sir, it shows good reproducibility. I checked the same result after 2 months, 3 months, and it was showing the same response.
Okay, thank you.
Thank you, sir.
Next participant, Arjun Rathod, Department of Physics, University School of Science, Gujarat. Are
Yes,
you
sir. Yes, sir.
Yeah, please share your slides
Yes.
and please stick to 5 minutes only.
Okay. My screen is visible, sir?
Yeah, Arjun, what's your poster number? It's PC37.
PC37, sir. Yes.
Yeah, you are visible. Please
Okay.
proceed.
So, good afternoon, all. My title of the poster is a strain-induced effect on the optoelectronic properties of half-Whistler alloy, LiGaSi. So, in this present study, we have used density functional theory with the generalized gradient approximation as implemented in quantum espresso code to investigate the electronic and optical properties with different induced strain. So I have selected the half-Whistler alloy, LiGaSi, which is basically crystallized in cubic structure with space group of 216 and F43M group. So we have calculated all the properties using thermo-PW code, which is also built in quantum espresso. And firstly, we have calculated the electronic band structure, and the result shows that our material LiGaSi is an indirect band gap semiconductor with the band gap value of 0.13 electron volt. As we apply 3% of tensile strain to the material, our band gap rises to the 0.18 electron volt. And as we apply minus 3% of compressive strain, it decreases to the 0.018 electron volt. Additionally, we have also calculated the optical properties, including real part of dielectric constant, imaginary part of dielectric constant, refractive index, absorption coefficient, extinction coefficient, reflectivity, and energy loss. So first of all, we have determined the real part of dielectric constant, which is basically related to the polarization of material. So here we can see that for the 3% of tensile strain, it shows the maximum peak in the region of near infrared to the visible region. And secondly, the imaginary part of dielectric constant shows losses of the incident light in the material. So here also we get maximum peak at 3% of tensile strain. Then after it gradually decreases. Then after we have calculated the refractive index, which is maximum for again 3% tensile strain. Then absorption coefficient alpha, which is maximum in the region in the energy region of 4 to 10 electron volt. And again it is maximum for 3% of tensile strain. And then after we have calculated the extinction coefficient, which shows the how much light attenuates in the material. So then after we have calculated the reflectivity. Reflectivity is above 0.5 in the region of 2 to 12 electron volt energy range. And then finally we have calculated the energy loss L0. it is maximum in the region of 12 to 18 electron volt. So the results of the optical properties and the electronic properties shows that our material is promising material for the optoelectronic application, because here we can see the absorption at 3% tensile strain. The maximum absorption is 200 into 10⁴ centimeter inverse for LiGA-Si material. So the results indicate that LiGA-Si possesses tunable electronic and optical properties under strain, making it a promising candidate for optoelectronic applications. Thank you, sir. Thank you for providing the great opportunity to present my poster. I am thankful to MIT University.
So Arjun, I have a question that how your imaginary part is affecting your outcome. Imaginary
Yes,
part, yeah.
yes, sir. So imaginary part, in the imaginary part, we can see that for the 3% of tensile strain, we have get the maxima about at 55. So as the dielectric, imaginary part of dielectric constant increases, the losses in the material increases.
Okay. And how you are accessing or characterizing your strength, strain? How you are calculating how much strain you are putting on your sample?
Yes, sir. For this, we have we calculated all these by the thermo PW code, and we change the seldom, which is the lattice parameter. We have changed the lattice parameter for 3% as well as -3% strain by the strain formula, general strain formula. Delta L by L is equal to वो जो formula है वो strain formula.
Okay, so if you change the material,
yes,
your energy loss will be changed. The peak value of the energy loss will also change.
Change the material or change the strain, sir?
Ah, yeah, sorry, change the strain.
Ha. When we change the strain, we apply at 0% strain, we can see the energy losses is nearly equal to the 5.5 at 0% strain. And for the 3% tensile strain, the energy losses increases. It becomes 6.5. And the for the -3%, matlab means compressive strain, the energy losses decreases slightly. So as we changes the strain, it will affect the energy losses as well as all the optical parameters and all the electronic parameters. So we can say that our material is tunable for this application.
So Arjun, you have done the simulation of the material, na?
I have done the DFT calculation, sir. First principle calculation
So
using on some equation.
Are you planning to verify the result practically in near future?
Yes, sir. I am planning to verify practically because this material is novel material. It is not studied so much. So we have calculated in the novel materials. Sir.
Yes, we suggest you to do the verification of the results practically. Okay.
Okay, sir.
Thank you so much.
Thank you.
Thank you, everyone. Is anyone left for his or her presentation? Thank you, everyone.
Done.
Excuse me, sir.
Yeah.
Sir, this is Lalita Deshmukh. Actually, my turn was on the first day, but because of some medical emergency, I couldn't attend.
No worries, Lalita. Please share your screen.
Yes, sir. Thank you.
And please tell your poster code.
PC04, sir.
Sorry,
PC04. 04 on first day.
Please share a slide.
Yes, sir. Is it visible?
Yeah. Kindly make in full screen mode.
Yes, sir. Yes, sir. It is on
And
full
please
screen.
stick to 5 minutes only.
Yes, sir. Yes, sir. Definitely, sir. So good afternoon to everyone. My topic is morphological tailoring of tin oxide nanomaterials for optoelectronic applications. So About the tin oxide, this tin oxide is a nanoparticle that is a SNO2 having a chemical formula. SNO2 is an N type of a semiconductor with a wide band gap near about 3.6 electron volt. This SNO2 is considered as an oxygen deficient N type of a semiconducting material. It is a tetragonal rutile structure. High optical transparency that material is having, low electrical resistance, where SNO consists of the two different types of phases, say SNO and SNO2. It has two types of oxide, that is a stannous oxide and the stannic oxide, with other phases such as SN2O3 as well as SN3O4. So SN2O2 has a greatest electronic band gap than the SNO at 300 Kelvin, which has a band gap of about 3.5 electron volt. So during this presentation, the orientation of my work is the morphological tuning is the most important factor that I have to tackle. So for that purpose, the hydrothermal method was adopted. The tin oxide nanomaterials was synthesized using hydrothermal method, in which the different concentration of tin precursors was carried out at a pH level is say 10 to 12. Then the synthesized nanomaterials was annealed at 600 degrees Celsius for 6 hours, followed by filtering and drying. And the morphological optimization was carried out by using the scanning electron microscopy. So this is the, I think, the pictorial representation in which the reaction that was carried out. First, I have been taken the source of a tin, that is the stainless chloride, in which the dropwise addition of NaOH maintain the pH between 10 to 12. Then that solution is transferred to a Teflon container, and then it is shifted to the stainless steel autoclave for the further temperature treatment. Then the temperature was maintained during the furnace, it's say 180 degrees Celsius, and the reaction was carried out for the duration of 24 hours. After 24 hours, natural cooling was done. That means after 1 day, I have been taken out whatever be the residue is there from the furnace, and that was filtered out. And again, for the crystallization purpose, it was annealed at 500 degrees Celsius for 5 hours, and I got the material. So the morphological feature of the synthesized material was carried out in relation with the three different concepts, perspective that we can say, in aqueous medium, in the alcoholic medium, and by changing the reaction time. So the first same image depicts the globular agglomerated morphology with irregular features, and that reaction was carried out having the tin precursor concentration is a 0.1 molar, and the reaction time is a 24 hours, and the pH maintained was 12. Then the second one, the molarity that has been taken out, it's a 0.08 molar of tin precursor. 24 hour is the reaction time, and the pH is at 12. Again, the globular agglomerated type of morphology was seen with irregular shapes. Then the 1.4 molar tin precursor that has been synthesized. So for the reaction time of 48 hours, that means increase in reaction time. There is a change in the morphology. This morphology depicts somewhat complex nanoflex or nanodealer type of an assembly.
Please be concluded.
Yeah. Yes, sir. Yes, sir. Definitely. And next, when the alcohol content is added, at that time, that drastic change in morphology was taken place. It comes up to say nanoflex as well as nanoneedle type of assembly that has been found out. So reaction time is say 60 hours, and the whole reaction was taken in the ethanol medium at that time. Morphology that was seen. So this is the conclusion of my work. This work demonstrates the tailoring of morphology of tin oxide nanoparticles using hydrothermal method. Three different approaches were used. The agglomerated globular morphology was seen for the sample synthesized in aqueous medium. Rise in temperature as well as the medium gives rise to the change in morphology towards nanoflex as well as the nano needles. Thank you very much, sir.
Yeah, Miss
Hello.
Lalita. Yeah, hello. Thank you, Miss Lalita. I have a
Yes.
question. I would just want to know that this type of work has been done by various researchers, even by using the hydrothermals also to making the needles-like structure or flakes-like structure. So what new you are looking into your research so that it can become into an outcome?
Yes, sir. Actually, I have to go with some of the application that is optoelectronics type of an application. So the morphology that I needed is either that optical features that I want. That means
So how you can utilize
visible.
your prepared material for particular type of
Yes, sir.
optoelectronics?
For photo detection purpose, I'm trying for this.
Okay, so what you are expecting for such type of structure that
Uh,
how your
no, sir.
photosensitivity will be?
Yes. Actually, expecting such a nano needle or nano wire type of a structure, sir.
Okay, thank you.
Thank you, sir.
Yes, sir. Thank you. Thank you, sir. Thank you very much.
Any participant left for his or her presentation? Thank you. Thank you, sir, for giving your valuable and precious time for reviewing the participants. We are very grateful to you, sir. Thank you, sir. So finally, we are having for the lunch. This is a lunch break. Thank you, everyone. There will be a next session after some time. Please, we are requesting all the participants to join the next session. Thank you, everyone.
Excuse me. Can you hear me, please?
Yeah, we can hear you.
Yeah, so the next session will start at 2:30 or it will be delayed? Oral session?
Yeah, ma'am. Just a moment, ma'am.
Yeah.
Yeah, ma'am. It will be started at 2:30, ma'am.
Okay, thank you.
Thank you, ma'am.
Mahima, be online. Am I audible, Mahima? Unmute yourself. Hello.
Yeah, hello. Am I audible to you?
Yes, ma'am.
So we have to start this oral presentations, but I think the time is 2:30 as per the
Yes, ma'am. Lunch is going on, so we will wait for 5
have to
minutes.
wait for 5 minutes, right?
Yeah.
Yeah, okay. So since I have a flight also, so I told Avshish, so in between if I have to go, please you kindly proceed.
Okay, ma'am. No issue.
Whoever is the moderator, kindly proceed.
Yes, ma'am. Sure.
Tell you.
Thank you, ma'am.
Okay, so shall we begin? Hello. Hello, organizers. Can anyone hear me? Hello, Mahima ji, can you hear me? Can you hear my voice?
Ma'am, I can hear your voice.
Okay. So I think you are the first one, OT09.
It's OT10, ma'am.
10?
Yeah.
Okay, but the schedule which was shared with me, it is 09 anyway. So are you ready with your
Yes, ma'am, I'm ready.
So let us ask the organizers if we can proceed.
Yeah, sure, ma'am.
So anybody from the organizers? Hello.
Good afternoon, everyone. Myself, Akanksha Deshwal, PhD scholar, MIT Institute of Nanotechnology. It is my pleasure to introduce Dr. Indra Sulania, scientist of an Inter-University Accelerator Center. She is the in charge of scanning probe microscopy facility, which includes AFM, MFM, STM, and CAFM modes, etc. Contact angles measurement setup, optical microscopy, and UV-vis spectrophotometer. She is in charge of material science beam line in BH1. Her areas of research interest are investigations of nanostructure, nanopatterns, formation on various materials, and thin films and their applications. Oxide nanoparticles, especially iron oxide nanoparticles, for their use in sensing and photovoltaic applications. Biosensors such as those for glucose and cholesterol detection using the composite films of various materials such as polymer plus oxide nanoparticles, etc. So, first, I would like to invite Dr. Mahima Shoran, Amity University, Uttar Pradesh, Noida. Ma'am, you have 15 minutes to conclude the session, and the platform is yours.
Thank you so much, Akanksha. Is my presentation visible?
Yes, ma'am. Full screen mode.
Is it visible now?
Yes, ma'am. You can.
Okay. So, my name is Dr. Mahima Shoran. I have recently defended my PhD Viva from MIT Institute of Nanotechnology. I have done my PhD under the supervision of Professor Om Prakash Sinha. The title of my today's talk is Recent Progress in Bio-Waste-Driven Carbon and Their Composites for Supercapacitor Applications. And my oral talk number is 10. So this is the outline of my presentation, which includes the introduction of supercapacitors, bio-waste-driven carbon, and need for the bio-waste-driven carbon and their various applications, introduction and their synthesis and optimization of their electrochemical performance. So to start with, supercapacitors are nothing but the basic intermediate between the conventional batteries and the conventional capacitors. They are a combination of having higher power density, rapid charging discharging abilities, long cycle life, making them essential for specific application where traditional batteries or capacitors fall short. So there is a need for supercapacitors as they will replace the traditional sources of energy. And right now, presently, we are highly reliable on the traditional sources of energy, that is fossil fuels. So to achieve a sustainable energy storage, we are more intended towards higher capacity energy storage devices, and supercapacitor is among one of those. So supercapacitors have various benefits over traditional batteries and capacitors, which include lesser battery size, which includes cost effectiveness, and there is no toxic emission of gases, or these offer high performance and extended battery life and a lifespan, and they can be varied upon various temperature range at extreme temperatures from -40°C to 70°C. So this figure includes the charge storage mechanism, the properties and application of supercapacitors. Supercapacitors in general are classified into three categories, that is EDLC, electrical double layer capacitors, pseudo capacitors, and hybrid supercapacitors. So in EDLC, there is accumulation of charge over the electrode surface, and in general carbon-based materials show the EDLC behavior. Other one is pseudo capacitors, in which there is a migration of ions between the electrode and electrolyte interface. So the hybrid supercapacitors are those which involve both the mechanism, that is the charge is stored electrostatically as well as electrochemically. This involves both the combination of EDLC as well as pseudo capacitance. As discussed previously, supercapacitors offers various properties, like they offer high capacitance value, they have higher energy density as compared to the common capacitors, as well as higher power density as compared to the conventional batteries. They are eco-friendly, they are highly reliable, and they can perform in variable temperature range of -40°C to 70°C. Today, supercapacitors are used in various household applications, like they are used in our cell phones, laptops, and other electronic gadgets which we use in our everyday life. So my topic is based on bio-waste. So bio-waste is generally the waste, any kind of waste that is of biological origin, and this typically includes food scrap, garden or park waste, food, vegetable peels, and other organic matter like wood, paper, or even animal and plant remains. So bio-waste can be decomposed naturally, or it is often used in compositing or bioenergy production processes. It is different from non-organic waste like plastic or metals, which cannot be degraded by, which is not biodegradable. So application of bio-waste driven carbon are mentioned here over here, that as we have discussed various type of bio-waste or biomass, we can easily synthesize carbon-based material using carbonization by either hydrothermal or higher temperature pyrolysis method. And these can be used in various applications like batteries, supercapacitors, wastewater treatment, catalysis, and air and gas purification, and organic LEDs as well. They are the electrodes made up of these bio-waste driven carbon are also used to generate bioelectricity. So presently, as we all know that in market, there is a commercially available carbon-based materials. These carbon-based materials are very expensive. They offer less specific capacitance value, and apart from that, they are high. They include higher complicated preparation method. They also, as mentioned over earlier, that EDLC or carbon-based materials show lower energy density as compared to the batteries. So the bio-waste driven carbon can replace the commercially available carbon-based materials, as they offer higher thermal and chemical stability. They are present in abundance. They are eco-friendly, and they have a porous structure which enables them ease of electrolyte accessibility. So various composites which include bio-waste driven carbon can possess cost effectiveness, better lifetime, cyclic stability, electrical conductivity, as well as they offer higher specific capacitance value as compared to the commercially available carbon-based materials. So these are the various advantages of using bio-driven waste carbon, as they offer large surface area with a good porosity and excellent electrical conductivity, and moreover, for charge storage mechanism, they offer ease of electrolyte accessibility. So bio-waste-driven carbon are synthesized using various methods. The most commonly used bio-waste synthesis method for bio-waste-driven carbon are hydrothermal method and general pyrolysis at higher temperature. So figure 1 involves the synthesis of carbon from various peels, which include onion, potato, and peas peels using a simple hydrothermal method, and carbon spheres were synthesized from this method. The second figure 2, shows the synthesis of high capacitive carbon material by hydrothermal processing, followed by a pyrolysis at higher temperature in inert atmosphere by activation of potassium hydroxide activation pyrolysis. This figure 2 involves the crushed sugarcane baggage, and from that we synthesize porous carbon-based material. So here, this figure shows the FESM image of the previously synthesized carbon sphere using different peels, namely onion, potato, and peas peels in figure 1. And this figure D to F show the various particle size of which involve the micrometer range that the carbon sphere obtained using this hydrothermal synthesis were of micrometer range, and namely the diameter of the range diameter of the carbon spheres were found to be nearly 1 micrometer, 4.5 micrometer, and 3 micrometer for onion, potato, and peas peels. Moreover, the EDX spectra also concluded the presence of the carbon and oxygen matter apart from any impurities in the synthesized carbon spheres over here. This figure 2 shows the FESM image of the carbon derived from the various method from pyrolysis, firstly by hydrothermal treated activated sample, or by simply prepare initial hydrolysis step followed by the activation by KOH. So these are the various method which involves the preparation of bio-waste driven carbon from hydrothermal or pyrolysis method. These figures show the electrochemical performance of the synthesized bio-waste carbon, bio-waste driven carbon. Here, figure 1 shows the CV curves of the various onion, potato, and peas peel driven carbon spheres. Here, at different scan rates, varying from 10 to 50 millivolt per second, and it can be seen that here from the shape of these curves, it can be seen that there is a EDLC, dominant EDLC behavior along with the pseudo-capacitive behavior. In general, the carbon-based materials show the EDLC behavior, but here the presence of the pseudo-capacitive behavior is also seen from the CV curves over here. This presence of pseudo-capacitive behavior may be due to the presence of the oxygen functionalities in the synthesized carbon spheres. Similarly, the galvanostatic charge discharge studies curves also showed the same kind of behavior, that is the dominant EDLC behavior was shown along with some pseudo-capacitive behavior, again due to the presence of the oxygen functionalities. Moreover, it can be seen that these bio-waste driven carbon spheres offer a larger discharging time as compared to the other ones. And here it can be seen that the higher, as we know, the higher is the discharging time, the better will be the value of the specific capacitance. Moreover, the cyclic stability was also studied for the synthesized carbon spheres, and it can be seen that almost a straight line was obtained for each sample, showing their higher cyclic stability up to 6,000 long cycles, and the values of specific capacitance were calculated at various current density varying from 0.1 ampere per gram to 1 ampere per gram, and it was found to be nearly 2,221.3 that was found to be maximum for potato peel driven carbon spheres over here. This is the comparison of the values of specific capacitance from some bio-waste driven carbon, which include neem, coffee shells, tobacco waste, and so on. These are some of the work which we have done on bio-waste driven carbon. These are our paper, which include an economical green root synthesis of carbon sphere derived from kitchen bio-waste for supercapacitor application. This is the work which I have mentioned earlier. And apart from this, we have also used the potato peel driven carbon spheres along with metal sulfide in order to analyze its behavior as electrode material for high performance asymmetric supercapacitor electrodes. And it can be seen seen over here that as we add a metal sulfide along with the potato peel driven carbon spheres, its value of specific capacitance increased, and which was found to be nearly 2185 farad per gram at 0.2 ampere per gram current density, showing its higher efficiency and a potential candidate for highly efficient and economical asymmetric supercapacitors. So to conclude with, it can be said that the biomass waste is a renewable and sustainable source of carbon, and it can be processed from various into carbon materials through activation, hydrothermal treatment, or pyrolysis treatment. And carbon activation for supercapacitors can enhance the surface area and porosity. Higher the porosity and the surface area, the higher will be its efficiency for ease for electrolyte accessibility. And so these offer low cost and eco-friendly carbon-based materials for supercapacitor applications. And as discussed over here, that the higher the surface area also leads to higher efficiency of the supercapacitor electrode materials, showing a high specific capacitance, longer cycle life, and fast discharge or charge rates. So it can be said that the bio-waste driven carbon materials are proved to be potential electrode material for energy storage systems in supercapacitors as well as other applications as well. So this is my work. Thank you so much.
Okay, so Mahima, can we take a few questions? Can you take few questions?
Yeah, sure.
Okay, so I would like to know that you have in your slide you have said that all kind of bio waste you are using. So I
Yes.
would like to know that how do you actually specify selective bio waste specification? How do you ensure? Because the degradation of different kind of peels is different, and
Yes, ma'am.
make them into carbon powder.
Yes,
So
ma'am.
how do you disintegrate, or you know what I mean to say is selectively, how do you ensure? What do you do to do that?
How I choose, ma'am, you are basically trying to ask how I chose my material to synthesize carbon from it.
Absolutely. Which material you use and how did you select? Because
Okay.
the
So
bio-waste consists of many kind of things, right? Here you
yeah,
have yourself.
Yeah. So, ma'am, basically, as we all know that we every day we cook everything in our kitchen, right? So there are a lot of vegetable waste. So from that got me motivation for it, that I have chosen a kitchen waste in our everyday life. I have chosen the potato peels and peels and onion peel, which can be used. We throw it like I have shown in the images as well that it is thrown every day into dustbin and garbage. And so it can also lead to an effective use of these bio waste from our kitchen waste. Apart from it, there are various other kind of waste which I have not used them, but I have gone through the literature reviews that we can also use eggshells, which are thrown in our everyday life. We can use garden waste, tree waste, and we can optimize those bio waste into essential electrode materials for supercapacitors.
Okay, and how do you carbonize them?
Ma'am, the carbonization method involves either hydrothermal treatment or pyrolysis at higher temperature in an inert atmosphere. So I have used both the methods. I have used hydrothermal method as well, and apart from it, I have used pyrolysis method as well.
Which one gives you better performance in terms of supercapacitor application?
Which method?
Yes, out of
Okay.
these two.
The carbon synthesized from pyrolysis method gives better efficiency, ma'am, because when you give it an inert atmosphere at higher temperature, because during a hydrothermal treatment, it can go up to only a limited temperature range, like 180 degrees Celsius or 200 degrees Celsius. But when you go to higher temperature, it gives better efficiency, and apart from it, you get better surface area when you pyrolyze
Okay, so I missed the stability of your samples. You did not mention that how stable are your samples with time, or means how do you ensure that they are not degrading?
Okay.
What do you
Ma'am,
think?
they are not, I have tested those samples like I have mentioned over here that I have tested those samples up to 6,000 long cycles. They were not degraded at then. The cyclic stability, we obtained a fixed value, almost a similar value of specific capacitance up to 6,000 long cycles. So
did you try to do it after 1 week of passivation or something like that, keeping it in shelf and then using it again for the measurements? Did you try to do that?
no,
Overnight,
ma'am, I
temporal
didn't.
kind of thing?
No, ma'am, I didn't do that.
Okay, and what is your supercapacitor value? Which you are saying that you are using it for those applications. So what is it, the typical value? I missed it in your slide.
Ma'am, it is mentioned over here and in the paper as well over here that the maximum value for a specific capacitance for potato peel driven carbon sphere was found to be 1987.5 farad per gram at 0.2 ampere per gram current density. While when we add nickel sulfide in it, it was found to be to 2185 farad per gram at 0.2 ampere per gram current density.
Okay, thank you. Very good work, Mahima.
Thank you so much, ma'am.
We can move to the next one.
Okay, thank you, ma'am. Should I leave now?
Akansha?
Yes,
over to you. Any other questions from the audience?
No, ma'am.
Okay, yeah, Mahima, you can
Oh.
unshare your screen.
Yeah.
Okay, thank you.
So moving ahead, I would like to invite Miss Rinki Agarwal, Amity University, Uttar Pradesh, Noida, to present her talk.
Oh.
Good afternoon, all. Hello. Good afternoon, all. Myself, Rinki Agarwal, and my today's oral talk topic is lead chalcogenide over silicon nanowire heterojunction based photodetector for IR radiations by chemical bar deposition. So these are the key points of my talk. First, synthesis of silicon nanowire using MACE, that is the metal-assisted chemical etching method. After that, mechanism of lead chalcogenide over silicon nanowire using CBD, that is chemical bar deposition. Importance of heterostructure, lead chalcogenides over silicon nanowire thin film.
Excuse me, Rinki,
Question of
can I interrupt you, please? So organizers, this presentation is not shared. I think it is not visible on my screen. Thank you. Yeah, Rinki, please proceed.
So lead chalcogenide over silicon nanowire heterojunction based photodetector for IR radiation by CBD. And these are the key points of my talk. So first, synthesis of silicon nanowire using MACE. So what is MACE? MACE is the metal assisted chemical etching technique. This is a very simple and sophisticated instrument and technique by which we can deposit or means form a nanowires over the silicon substrate. So here we use P-type silicon, and first we clean up with the ethanol acetone by 10 minutes each. And after that, we deposit in a etching solution that is prepared in a Teflon beaker. We are mentioning that is 0.02 molar silver nitrate and 4.6 molar hydrofluoric acid at a room temperature for 1 hour. So figure 1 shows the schematic or steps of silicon nanowire formation, and figure 2 shows the SEM view. First one is top view image, and second one is tilted side view image. Now, synthesis of lead chalcogenide over silicon nanowire using CBD. Again, the figure 3A shows the apparatus in which we kept our substrate that you can easily see in it. And we can moderate it temperature or time, at which temperature we have to kept our substrate. And figure B shows the schematic, how the substrate is put and how the chemical reaction take place inside it. So basically in CBD, there are two mechanisms, cluster mechanism and ion by ion mechanism. Cluster mechanism is performed for low temperature. In this, the substrate has no role. That is a chemical compounds or complexing agent plays a role, and they accumulate inside the solution itself. But ion by ion mechanism is used for the high temperature, and in this mechanism or reaction take place itself over the substrate. Now the importance of heterostructures metal chalcogenides over silicon nanowire thin films. So basically the nanowires is a one-dimensional vertically aligned thin films, and it's good because it gives an enhanced performance due to the interfacial area, and it provides an excellent template for the fabrication of diverse heterojunctions. These silicon-based nanostructures has various importance and properties in optoelectronic devices because it has higher surface volume ratio, which greater than the active sites at the material surface. Now the discussion how the lead sulfide over silicon nanowire for self-power photodetector we have made. The figure 4 demonstrates the schematic view of lead chalcogenides. First one shows the silicon nanowire formation, and after that, lead chalcogenides cover the surface completely. And B1 shows our electrical measurement. We use Cathode electrometer to measure the IV characteristics. And figure C shows the SEM image, and we can easily see that the lead chalcogenides cover the silicon nanowires completely. And this one shows the photoelectric response for on-off cycle in the presence of trisodium citrate with IR radiation. That figure A shows on-off cycle, and B is the zoom image of one cycle, in which you can see the time rise is 1.6 second and fall time is 0.53 second. And the C1 shows the electric response against the filter. We use 4 filters, 640 nanometer, 780 nanometer, and 1046 nanometer. And the D1 shows the photocurrent generated. We calculate this photocurrent by a C graph. And after that, we again calculate the responsivity and detectivity of our photoelectric response in on-off condition by varying the photo intensity. Like we vary the distance between the light and the sample. So it shows in figure A, you can easily see as we vary the intensity of our light, so the graph is decreasing. B1 shows the responsivity and detectivity. Again, that photocurrent generator against the voltage. First, we shows the photocurrent generator with intensity, And after that, we plot the graph with bias voltage. So why we called it as a self-powered? Because without giving any bias voltage, in figure C, you can see at 0 voltage, it shows some photocurrent. That's why we called it as a self-power photodetector. Now, let's selenide. First, we talk about the lead sulfide over silicon nanowire. And now it's lead selenide over silicon nanowire. So we again check it or detect it for a NIR range. That is a near infrared region. So figure 7A and B shows the same image. The first A and B shows the lead selenide over the silicon surface, and C and D shows over the silicon nanowire substrates. To compare the difference of the substrate of the result, we take two substrates. First, only a bare silicon substrate, and another is silicon nanowire substrate. And thus E1 shows the XRD of this data. Again, we took the electrical characterization of this, and you can see that first one shows the IV characteristics under the presence of light and dark, and the second one shows its photocurrent comparison with different wavelength 640, 780 and 1046 with two different substrates, which is lead selenide over silicon and lead selenide over silicon nanowire. And what we conclude? We conclude that lead sulfide over silicon nanowire gives a good self-power photodetector result. As the third point gives photocurrent of approximately is about 2.5 microampere, and a photovoltage is around 780 millivolt at 0 volt, which gives that it's a good device or a good source to be a self-powered mode. And it also gives a responsivity is around 0.21 ampere per watt, and detectivity is around 6 into 6 multiplied with 10 raised to power 9 joules under the 1064 nanometer wavelength. And lead selenide doesn't give a good result for the 0 volt bias, but it gives at a 1 volt bias. So this work immense the application in the field of large scale fabrication of self-power photodetectors based on rational design of p-n heterojunctions using nanomaterials. So these are my publications, and 3 are published and the 4th one is under preparation. I acknowledge to SERP for giving us project for this, and also my guide Sucheta Sen Gupta ma'am to help me over every step, and Dr. Neeraj sir, Nitesh sir and Vivek sir over helping me in my lab work, in everything. And again, IIT Delhi and INUP program for characterizations. Thank you. And any questions?
Yeah, okay. So, Rinki,
Yes, ma'am.
very nice work. So, I have like 2-3 questions for you. So, why did you choose the lead chalcogenides here? Because you know it's a toxic in nature. So, how do you answer the toxicity in your samples?
Ma'am, lead chalconide because it's good for the IR detections. That's why we use lead chalcogenides.
But do you know it is toxic in nature?
Yes, ma'am, but we didn't use that much amount it will toxic to anyone. We use barely little bit or 0.01 molar around.
No, this is not the answer. Do you have any alternate to these samples?
Yes, we have a cadmium sulfide we can use.
Okay, so what is the figure of merit? Like, did you do some thermoelectric properties also for the power generation from your samples?
No, ma'am.
Okay, so out of these two heterostructures, like lead sulfide, lead selenide and lead sulfide, which one is performing better and why?
Lead sulfide is performing better because it gives a good connectivity with silicon nanowires as it transfers the charge transports and makes a good heterostructure bonds That's why it gives the good result at 0 volt.
Okay, one last question. You did not do any kind of mapping characterization. So how do you ensure that lead sulfide has actually capped the silicon nanowires?
Ma'am, we did a EDEX
But
mapping
EDEX
also.
is completely doing it on some area, right? Did you do some mapping? Mapping especially to show that silicon nanowire is inside and then lead sulfide is
Yes, ma'am.
outside?
Yes, ma'am.
Which measurement did you perform?
We perform XPS and TEM.
TEM you have performed, but you have not shown here.
Yes, ma'am.
Okay, Rinki. Thank you. Thank you for your...
Thank you, ma'am.
Can move to the next one if there are no questions from the audience.
So next, I would like to invite Mr. Nitesh Kumar, Amity University, Uttar Pradesh, to present his talk.
Thank you for inviting me.
Okay, please share it also, okay? So that I can see the slides.
Good afternoon, all of you, and good afternoon, ma'am. My name is Dr. Nitesh Kumar. I did my PhD from Amity University in Materials and Devices under the supervision of Dr. Suman. Today, I'm going to present my research topic, a portable handle device for detection of heavy metals and microbial contamination in water. Basically, this is the background. Metal contamination is a major concern to human health nowadays, and also the microbial contamination is a major health concerns. We basically coliforms are present in the water, contaminated water, and which can be shown as indicator organisms, which indicate the existence of contaminant present in the water. So we need to develop some system to detect the metal contamination or as well as microbial contamination. So basically, a source of heavy metal contamination is coming from mining, corrosion, metallurgical industries, agriculture sources, smelting, and leather tanning, majorly leather tanning and dye industries. And worldwide scenario of the waterborne disease is 37.7 millions. Every 2 minutes, a child dies due to the poor sanitation or poor water quality. So the heavy metals are in water majorly present: chromium, lead, arsenic, barium, strontium, and cesium. These are major concerns for the drinking water, basically. And the existing methods available for the detection of heavy metals is atomic absorption spectrophotometer, inductive coupled plasma ICP, which can call as ICP, and X-ray fluorescence spectrophotometer. But these instruments are very costly, and it will cost around 4,000 to 5,000. And it's required also sport personnel to operate these instruments. And for existing method for detection of microbial contamination is a plate culture count. So this is a basic standard method. And Colifast alarm test is also one of them, which can help to detect the microbes. But these methods are mostly reliable, but takes much time to detect. So it will around take 24 hours, which requires incubation times. And it also requires a lab expertise to handling and operate these systems. So basically, I have a plan to develop such system which is able to detect the microbial contamination, heavy metal contamination in a few minutes or seconds. So what I have methodology adopted: first, the selection of nanomaterial, and this is silver nanoparticle and gold nanoparticles. Because these nanoparticles are usually easily modifiable, we can easily functionalize by different functionalizing agents. and it it shows no interference effect with other heavy metals because it has better selectivity. So for detection of heavy metals such as chromium, I have synthesized citrate cap silver nanoparticle by using the method where use silver nitrate and sodium borohydride, which is highly reducing agent, which form the nanoparticles. And simultaneously, I have also used sodium citrate, which is able to functionalize the nanoparticle, silver nanoparticle. So this is very specific for the detection of heavy metal, that is chromium. And this is the image of heavy metals detection mechanism. First image shows the cellular nanoparticle, bare cellular nanoparticle, which is functionalized by citrate. And when we add few drop of chromium containing water, it will convert into red colors. So this color will be easily detected by naked eye. But for quantification purpose, I have developed a system which is able to quantify how much concentration present in the sample. So this is the optimized assay for detection of chromium in metals, in heavy chromium contaminated water. This optimized condition is pH around 7, pH around slightly basic, pH 8. Temperature was optimized at 25 degrees Celsius, and incubation time was around 30 to 30 seconds to 1 minute. We can measure the concentration range 10 ppb to 1.5 ppm. And the volume of optimized nanoparticle was 2.7 ml and the volume of sample of 0.3 ml. So with the optimized condition, I have optimized these system with the least level of detection of 26 ppm. So sorry, 26 ppb. This paper is only published in the Journal of Environmental Chemical Engineering. That was impact factor of 5.9. And this is the selectivity study of nanoparticles. This is highly specific for only just chromium 6 and chromium 3. So here we can easily observe that there was no interference effect of other heavy metals present in this method. This is the calibration graph by which I have calibrated the device for standardize the system. We have taken different sensor value from starting from 0.01 ppm to 5 ppm and standardize the device by using these equations. These equations are already put in the calibrated graph by incorporated into this device. So determined concentration of unknown sample was also optimized and determined by the flame atomic absorption spectrophotometer. Here we can observe the various metal concentrations, and there are 3 unknown sample concentrations which we have detected by the flame AS as well as our handle device. So there's unknown sample of 1, 2, and 3. They're approximate 0.9 ppm and 0.84 ppm observed by our device. So basically very similar to the standard, well-known standard method. Now comes on the detection of E. coli or microbial contamination. So here we have used the gold nanoparticle. Gold nanoparticle has been functionalized by the cysteine, which is an amino acid, and it changed the color from red to violet. So we can easily detect by a naked eye. We can easily observe by naked eye, but for quantification, we have developed this device as well. So this is the mechanism by which we have synthesized gold nanoparticle. We have used the gold auric chloride and trisodium citrate, which is also used for the capping of these nanoparticles. And functionalized nanoparticle wise was also functionalized by cysteine, which is an amino acid, around 10 power minus 5 molar concentration. So this is the mechanism by which we can detect the E. coli present in the sample. Firstly, I have synthesized nanoparticle which is functionalized by cysteine, and cysteine cap, we can here observe the SH sulfur bond bind with the nanoparticles and free ammonia, free NH3, NH2, NH3 bond plus available, which provide the positive charge of the nanoparticles. But when the E. coli, which is I assume that is negatively charged, bind with the positively charged nanoparticles, will form the agglomeration, and this agglomeration leads to the formation of color change, yellow from violet. So this is visible by naked eye, and for quantification, we have used the device. This is the characterization structure, characterization tables of figures of these nanoparticles, pure E. coli cultures and gold nanoparticles, functionalized and unfunctionalized form both. And we have also analyzed the comparatively detection of E. coli in conventional method. We can observe here the conventional method, there's a plate culturing counting around requires 24 hours, and coli alarm test require around 22 hours. Similarly, coli alert test also require 18 hours. RT-PCR is also there to detect the microbial contamination, but it will also take 2 to 3 hours for operating the system. But our method is very reliable, and it requires just 30 seconds to develop the color, and we can easily measure by the device. This device we have developed is a schematic diagram. We have used the LDR microcontroller processing, and we have used also LED, which range around 520 nanometers, because the nanoparticles lies between these this range. So this is a schematic diagram of our developed device. We have functionalized here gold nanoparticle by 16 to develop detection of E. coli. Similarly, polyethylene glycol will functionalize to detect for arsenic, and silver nanoparticle is functionalized to synthesize citrate cap by for detection of chromium. This device also patented. We have filed the patent in 2017, and now this is granted. Just in January, we have granted this. We have obtained this grant of patent. Also, this device can be modified to detect further heavy metals and microcontamination in terms of lead, barium, strontium, cesium, chromium, and other submicrobial contaminations. This is our team, Dr. V.K. Jain sir, who guide us to develop this device, and Dr. Devendra Milwal is basically from electronic background. He developed this device for special detection purpose, and Rupesh Basniwal sir is also there, and Mr. Verma is also motivating us. And this is the device display, and I thank you, AIRS, AIRE teams, and also ICST organizer teams. Thank you.
Okay, so very nice work, Dr. Nitesh. So I would like to just have some understanding of few concepts. So
Yes,
you
ma'am,
said
sure.
that you have formed citrate capped silver nanoparticles to detect the chromium 3+ and 6+, but in nature, how do you ensure that these polarity will be only available for the chromium ions as a
Because
heavy metal contamination?
yes, sir, we have also tested the interference effect. Here we can observe. We have tested lead, zinc, and so on, heavy metals. But basically, we just identify the chromium 6 and chromium 3, because chromium 6 basically reduce to chromium 3, which finally bind with citrate cap ions. So chromium 3 is very specific for the this nanoparticles. So we can say that chromium 3 and chromium 6 is only detected by this device.
So here, as I understand, only citrate polarization is important to bind with this 6+ and to make it 3+ or so on. So what is the significance of using silver? Why not any other metal?
Sorry, ma'am, I'm not getting it.
Instead of silver, can't you use any other metal? What is so specific about the silver nanoparticles?
We have studied with other heavy metals, and we have studied different data from available literatures. And on keeping on in mind, we have optimized these conditions for this particular metals.
Okay, I think you have used it for gold also, isn't it? The right side one is showing you for the gold,
Yes, ma'am.
and left side is for silver. So which
Yes,
one
yes.
performed better? Silver one or the gold one?
Gold one also will there, but the detection limit was not observed as 26 ppb. So we have used here silver nanoparticle, which is very specific, and color differentiation is very visible for this device because it's colorimetric device.
Okay. And what kind of sensor it is?
Yes.
What kind of sensor it is? It is an optical sensor
Yes,
or
ma'am. Yes, it's an
electrical?
optical sensor based on absorption.
Okay, very good. And how do you detect the E. coli? Because you have shown that this turns from red to violet.
Yes, ma'am.
Okay. So, have you thought of using them as antigen strips to detect E. coli?
No, ma'am, we have not used this. We have just developed this gold nanoparticle functionalized with 16, and this color change due to agglomeration of the nanoparticle with the presence of E. coli.
No, I mean to say is in the market also, did you try to make a strip kind of detector out of it? Like we have with this RT-PCR and antigen kits are there, right? In the market, detect some of the things. So for the E. coli detection, what are your steps to perform to make it as a sensor or antigen strip to detect E. coli? Are you thinking about in that
Yes,
direction?
definitely, man. We have also tried to form a strip-based test, but we are not successful in this area.
Okay. Nice work, Nitesh. Thank you.
Okay, ma'am. Thank you so much.
So next, I would like to invite Mr. Neeraj Gupta, Amity University, Uttar Pradesh.
Yeah, good afternoon, everyone. Ma'am, my screen is visible to you?
Yeah, I can see that. Please proceed.
Yeah, good afternoon, everyone. First of all, I'm very thankful to the ICST 2024 for giving a platform to show my research. Myself, Dr. Neeraj Gupta. I'm from the AIIS department, and my topic is solar thermal energy storage material and its application. Yeah, as we all know that we are on the era of the 21st century. At this century, we required a huge amount of energy because there is a rapid modernization of industrialization and civilization take place. At present, as we all know, that the current energy sources are the fossil fuels. But as we all know, these fossil fuels have a very limited sources, and these fossil fuels also have a bad impact on our environment. So we have to look to the other different sources, renewable energy sources. If we consider renewable energy sources, we have different types of sources like we have wind energy, solar energy, geothermal energy. But out of those, we can utilize the solar energy. Why solar energy? Because it's a very cleaner, enormous. And if we talked about the India, we are very blessed that we have sun almost throughout the year. So we have to, and even if we talked about the Indian government also, now Indian government are also giving so much of funds to use the solar energy. And so if we try to use the solar energy, we can use the solar energy in two ways. The first way is either we convert the intensity to the light to the electricity, that is we can convert through the solar photovoltaics, and the second way is the either we convert the intensity or the radiation to the heat. But if we talk about the present scenario, the solar energy is also in the intermittent nature. Like we have the sun during the day, but we don't have the sun during the night. So what we do, so if we consider such type of solar thermal energy system, we can utilize which can use the solar energy. We can store the solar energy during day, and we can retrieve that energy whatever we need, maybe the daytime, maybe the night time. So that will be beneficial for the society, for the human society. So these are the things where we need the solar energy systems. These are the things where we need the solar energy harvesting systems. So if we talked about solar thermal energy storage system, the latent heat thermal energy storage system using phase change material are one of the one of the most current research areas for the solar to utilize the solar energy. What are the phase change materials? The phase change materials are the latent heat storage materials. The phase change material absorb the large amount of energy to the surroundings and remain constant or the nearly constant temperature during the phase transition process. If we talked about the phase change material, the phase change material are categorized into the four things that can be depending upon the phase transition. The first transition can be considered solid-solid. The second one is solid vapor. Third one is liquid vapor, and the fourth one is solid liquid. Out of four these, the solid vapor and the liquid vapor, even though they have the very high latent of energy, but we can't utilize them for the practical application. The reason is because they need a very large volume, and we are not able to handle the vapor pressure. And in fact, if we talk about solid-solid, this solid-solid have a very low latent energy. So we are currently working on the solid-liquid phase transition process because they have the good latent heat, easy vapor pressure, and easy to handle. See, if we use the PCM in a thermal system, there are some challenges with us. The first important challenge is the phase change materials have very low thermal conductivity. Because of low thermal conductivity, they have very low melting discharging rate, and basically the phase separation takes place in the case of the salt hydrates. And the salt hydrates have very disadvantages. They have the very incongruent melting, supercooling effect, leakage problem, and the hardening of the PCM takes place at the solid states. And we have some other thermophysical property that has to be enhanced. So how can we enhance the thermophysical properties of the PCM? The best and the simple and the economical way is to use the nanomaterials to make the PCM composites. If we talk about nanomaterials, we have different types of nanomaterials. We have metal oxide, carbon-based materials. So why we are using the nanomaterials? Because these nanomaterials have very innately high thermal conductivity as compared to the base PCM. If we talked about the carbon materials, the carbon material has 3000 watt per meter Kelvin to the 6000 watt meter Kelvin. So our main aim is to use the metal oxide or carbon materials to enhance the thermophysical property of the base PCM and to study the effect of these nanomaterials on the properties of PCM. If we prepare the composite, what are the desirable properties we need for the thermal energy systems? We first of the most important properties we need the high thermal conductivity. The second one, we need the high latent heat. Obviously, the material should be the low cost, and the volume. If we talked about the space, we need a small volume change. And if we use a nanomaterial, what the properties of nanomaterials are which affect the thermophysical property, which affect the thermal conductivity. Maybe the nanoparticle concentration. The concentration of nanoparticles play a very important role in enhancing thermal conductivity, even the size, temperature. These are the few properties which affect the thermal conductivity. So, see, if we talked about the carbon materials, as I told right now that we have the thermal conductivity of the carbon materials are 3000 watt per meter Kelvin to 6000 watt meter Kelvin, and we have variety of carbon materials like we have CNT 1 dimension, we have carbon sphere 0 dimension, we have graphene 2D. So our main aim is to see the shape and size effect of the carbon materials. So for that, we have choose the different types of carbon material. You can say at the figure A, we have choose the carbon sphere. B denote the multi-wall carbon nanotube. C denote the graphene nanopellets. D denote the nanographite. And the E denote the mesoporous carbon. What method we have used to prepare the PCM nanocomposite? We have used a metal mixing technique. In this technique, what we are doing, first we are hitting the PCM above the phase transition temperature. Then we add the carbon materials, stir it. Then we allow it to cool down. During the stirring process, we also doing the ultrasonication just to have a better dispersion of the carbon material in the PCM. Then ultrasonic. Then we do the at the last we allowed the PCM, the composite, at the room temperature to cool down it, and we analyze the thermophysical properties of the PCM. See, our first and the most important aim is to enhance the thermal conductivity, because if we able to enhance the thermal conductivity of the PCM, so we are having a enhancement rate of heating and melting. If we have a good heating and melting rate, so what happen? We are able to store and really we are able to store the energy in a very fast way, or we have a very high thermal charging. And another way, if you want to release the energy, if you want to take the energy from the system, the rate of the transfer of energy will be high. So you can say so what we have done in the figure A, we first use the PCM and we added the different weight percent of the carbon sphere, starting from 0.1 to 1.5 weight percentage. And then from the 0.1 to 1.58%, we have found that 0.58% is the optimum condition to have the maximum to have the thermoconductivity. Then further, what we have done, we fix the 0.8 concentration of the carbon material, and we analyze this carbon sphere with the other types of carbon materials, that is magnesium, that is nanographite, graphene, mesoporous carbon, MWCNT, and the carbon spares. See, if we talked about the values of thermoconductivity, as you can see, the pristine MH, that is a salt hydrate. The thermoconductivity value of the pristine MH is 0.4. But when we go from 0.1 to 1.58%, the thermoconductivity increases from 0.56, 0.6, and the last one is 0.9. If we talked about the terms of the percentage, the percentage enhances from 1%, it is 40 to 128%. See why we have chosen the 0.58%. If we see the enhancement factor from 0.5, from 0.1 to 0.5, and from 0.5 to 1.5, we have seen the enhancement factor is more profound in the range of 0.1 to 0.5 than to the 0.5 to 1. So that's why we have fixed the weight concentration, that is 0.5. And now, after getting the thermoconductivity of the 0.5 weight percentage of carbon sphere, that is 100% attachment, we compare this value to the other carbon materials. So as you can see that if we have fixed the concentration in the concentration of carbon materials as 0.5, and we have compared the values that carbon sphere, MWCNT, mesoporous carbon, graphene nanopellets, Ng, and carbon black. So we can see that the carbon sphere enhance the maximum thermal conductivity at the 0.58%, which is an improvement of around 100% as compared to other carbon materials. So from here we can see that out of different shape, if we talked about 0, 1D, 2D, the carbon spheres enhance the maximum thermal conductivity at the same weight percentage. After enhancing thermoconductivity, see, we have to do the energy analysis, because see, if we added the carbon materials, on the one hand, we are increasing thermoconductivity, but when we added the carbon material, do we degrading the energy storage property of the PCM? Because suppose if we enhance the thermoconductivity up to 100% and we decrease the energy storage property of the base PCM from less than 50%, so there will be no use to enhance the thermoconductivity of the PCM. So for this, we go for the DSC analysis. So what we have seen when we add the when we go from the weight percentage from 0.1 to 1.5, at the 0.5 weight percentage, the latent heat of melting, it was 146 values, but at the 0.5 it was 138. So what we have seen that there will be the less change, but the values are very less. Almost we have see that from 146 to 138. So there will be no more degradation what takes place in the energy storage property. And the most important thing, if you talk the MNS, there was a supercooling was about 25 degrees centigrade, but in the case of 0.5, we got the 6.3. So it is one of the prerequisites of a salt hydrate to have the low supercooling. Another thing, as we have seen that we at the spherical shape, we get the maximum thermal conductivity. So what we have done, we have used the TiO2 nanoparticle. The size of TiO2 nanoparticle was around 50 nanometer, and we compare the TiO2 nanoparticle with other carbon material, that is ZNO, Fe2O3, and the SiO2. So again, you can see the heat transfer characteristics when we add the TiO2 nanoparticle for 0.2 to the 1 weight percentage, the melting time was decreased. It was around 50 minutes, and when we added 1, it was around 30 minutes. So similarly, in the case, you can see in the case of the solidification rate, here again we can see that when we compare the TiO2 nanoparticle 0.58 percentage with the other metal oxide nanoparticle, again we can see that TiO2 nanoparticles, which is in the particle size, in the less particle size, which is around 50 nanometer, have the maximum thermal conductivity enhancement as compared to the other metal nanoparticles, whose has the particle size around 100 nanometers. So from these two studies, we can say that the spherical size nanoparticle enhances thermal conductivity more, and in compared to the size, Lesser the nanoparticle will enhance the maximum more thermal conductivity. So again, we have, you can see the results at 0.5, the value was 0.99. And in the case of other nanoparticles, so you can see that again, TR2 has the maximum thermal conductivity. One of the most important problem we are facing nowadays, that when the PCM solidify, it become hard. So to solve this problem, we are moving to the eutectic PCM. What we have done, we use the coconut oil because it's a organic PCM, and we use the paraffin. So we add the coconut oil to the paraffin, and we form the eutectic PCM. And what we have found that adding the coconut oil will soften the base property. We soften the paraffin. And to enhance the thermal conductivity of the eutectic PCM, we use the EG graphite. Again, if we check the FTIR curve, whether when we add what the composite, what the problem is taking, like how the interaction is taking place. So if we take the paraffin wax, FTIR and coconut oil, and we compare the eutectic PCM, we can find both the peaks of coconut oil, the paraffin wax, and we add the EG in the eutectic PCM, we find all the peaks. So this shows that there will be no any chemical mixing taking place. It was all about the physical mixing, and we can find all the peaks. So no new peaks was there. Then we have done the real-time experiment. Real-time experiment. What we have seen when we do the real-time experiment, the TR2 nanoparticles at the 1 weight percentage takes 7 minutes to melt down completely. In case of carbon nanospace, it takes the carbon space 4 minutes, while the pristine PCM takes 27 minutes. See, during the summer season, the person who is riding a bike, they have the very feel heat inside the helmet. They are unable to concentrate. In our lab, we have developed the PCM pad. When you put the PCM pad below, above your head and below the helmet, the temperature inside the helmet is constant for about 2 hours. That is 37 degrees centigrade, which is close to the body temperature. That is the skin. See, now one of the most important application we are doing. See, at the Ladakh or the high Lees area, what we have, we don't have the electricity over here, but we have a sun over there. So by using the phase change material, if you are able to develop the room, which can provide you the heat inside the room by absorbing the solar energy, so it will be most beneficial for the person who are living in the high altitude area. And not only the person, but even for the army people, where they don't have the electricity. So what we have done, we developed a prototype. This figure shows the middle figure shows you the room, where above roof we have developed a flat plate collector, and we remove the roof of the house, and we put the flat plate collector, and inside that flat plate collector PCM, it contains the PCM. And you can see some glimpse of the prototype, how we are doing. You can see the results. See, what we have find by doing the experiment, that when the sun is there, you can get the heat, and the temperature rises inside the room, that is about more than 45 degrees centigrade. Even though when sun was there, the room was able to maintain the heat near about 2 to 3 hours, or even more, depending on the mass of the concentration. So for this, we can say that for near about, you can say from 0 to for at around 50 minutes after, you can have the temperature near about more than 45 degrees centigrade up to 300 minutes. So this is some inside result. The S1, we have like this side wall temperature inside the room. S2 is the open temperature, sensor of the coils, and the PCM temperature composite. So from here you can see that when we switch off on the fab, this is a condition what we have taken place to have a uniform environment inside the room. Even though the temperature increases for
Neeraj, can you please wind up? I think we
yeah,
are running
even
out
these are the microwave shell feature what we are doing.
to the conclusion, please.
So even we are working on the jacket for the army people. These are some prototypes we are doing. Yeah, thank you. I'm very grateful to all my team members, and even my mentors, Professor VK Jain and Professor PK Bhatnagar, sir. Thank you, ma'am.
It's a very nice work. You have actually presented well, also building up from the introduction and then going towards your application. I have a few queries which I would like to understand. So you have emphasized the role of spherical shape in your material.
Ma'am,
So if you will not take spherical, if you take some other shape, say rod or something, what will happen? What do you be so specific about that shape?
Ma'am, as you see that in the carbon materials, we have used a different type of shapes like CNTs also. We have used 2 dimensions also, graphene, mesoporous carbons, and we have the use carbon sphere. So even our main aim is to check see the effect of the shapes of the carbon material in the base PCM, that is the magnesium nitrate hexahydrate. So from there, we have seen that when we increase the weight concentration of each particles at the 0.58% of carbon sphere, we find the maximum enhancement. That was 100% enhancement. And we compare this concentration or this shape, that is spherical shape, with the other carbon materials, even though we find that the spherical shape enhances the maximum thermal conductivity.
And what do you think? What do you suggest? Why is it so?
Ma'am, yeah, basically the dispersion, you can say the dispersion was better in the case of the spherical carbon particles, and even the perforation limit was very high in the case of the carbon spheres, and the again what we say, the boundary, the interface resistance between the matrix and the carbon material was very low in the case of the carbon sphere.
Okay, so in the table which you have showed, I could not see much differences in your values of DSC.
Yeah, ma'am, that's the thing.
So, but you are saying that it is very significant. So where is the error bar here?
Sorry, ma'am.
Where is the error bar in your DSC parameters? Yeah, here in the temperature, melting point, and all
Yeah,
those.
ma'am, you can see if we talked about the pristine MNH, the pristine MNH has the melting temperature was around 91.5 degrees centigrade, and it solidified at a 66.5 degrees set. So we can say our material was melt at a 90 degrees centigrade, but when it melt, it absorbed the energy, okay, for a system. But when we want that energy, so we want that energy at the 90 degrees centigrade only. But what we have seen the MNH, we are not able to get the energy 91 degrees centigrade. We are getting the energy when the temperature goes to 66 degrees centigrade. So it's a very lag between a system, because you want a system which work at a particular temperature. So this factor what we call the supercooling effect. And when we add the nanomaterials, so we can see this 25 degrees centigrade, which was the supercooling, it goes down to the 6 degrees centigrade, which is the one of the good thing for a system. And if we talked about the DSCs, ma'am, see, because when we add the nanoparticles, they do not contribute to the DSC portion. So we have to balance the weight percentage of carbon of any metal or nanoparticle in such a way we can enhance the thermal conductivity, but on the other hand, the energy storage property will not be degraded. मतलब कम नहीं होनी चाहिए कि ऐसा नहीं कि हमने थर्मल कंडक्टिविटी इनकी थर्मल कंडक्टिविटी हमने 100% बढ़ा दी और एनर्जी स्टोरेज प्रॉपर्टी हमारी 50% डिक्रीज हो गई. So as you can see that in the carbon sphere, the latent heat of melting was around 146. But when we add the carbon particles, it was around 144, 141, 138. So the values are very the change is very minimal, ma'am. We can bear this change.
Yeah. Okay, so at one slide you have shown the TiO2 melting, but do you know that melting temperature of TiO2?
I'm not able to recall right now.
Means it is very difficult to actually melt it, conventional way.
The thing is that we are working in the range of room temperature to the 90 degrees centigrade, and I think in that case TiO2 doesn't melt. So
yeah, it doesn't melt. So, but you have shown the melting. I think if I heard it correctly, I don't know, maybe.
No, ma'am. It was ma'am. This is the heat transfer characteristics.
Okay.
These, when we added the TiO2 nanoparticles, ma'am, in a base concentration, what we have seen, the black curve, ma'am, you can see the black curve take the 50 minutes. But when we add the TiO2 nanoparticle, the red one 0.2 weight percentage, the time reduces from 50 minutes to the 45 degrees centigrade. So this shows when you add the TiO2 nanoparticles, these TiO2 nanoparticles enhance the thermal conductivity, which in turn you can see the heat transfer rate has been enhanced. Previously, your material was take 50 minutes to complete its melting to reach its melting point. But when you add the TiO2 nanoparticles, now it's taking only around 45 minutes. So this shows your heat transfer rates has been enhanced by using this type of nanomaterials, ma'am.
And how many cycles did you use this?
Ma'am, we have done for each sample. We have gone at least 5 to 6 times. Like for the 0.1 percentage, we have go more than 5 to 6 samples. And then at the last, when we find that 0.58 percentage is the optimal condition, even just to check the long-term thermal stability, we have done the more than 50 heating and cooling cycles. Yes, ma'am.
Okay. Okay. Thank you. Very
Thank you,
nice.
ma'am.
Yeah. Okay. So we can go to the next one. Omita Nanda.
Yes, ma'am. I'm just sharing the screen.
Yeah, Omita, can you tell me your this number of your oral?
Ma'am, it's OT13.
OT13. Okay, so fine.
Is the screen visible?
Yeah, I can see it. Please carry on.
Ma'am. Good afternoon, everyone. First of all, I would like to thank all the committee members of the ICST for giving me this opportunity to present my work. Myself, Dr. Omita Nanda from Amity Institute of Advanced Research and Studies. And I'm here to present my work, and the title is Comparative Study of Fabrication Techniques for Thin Films of Reduced Graphene Oxide. So as we know that graphene is one of the strongest and the thinnest material, and it has various applications in different domains ranging from energy storage, electronic devices. Graphene membranes are there. It is used in composite coatings, sensors, biomedical applications it has. So, various derivatives of graphenes are available, which ranges from like graphene oxide and further going to reduce graphene oxide. So here we are working on, right now we are working on the graphene and reduced graphene oxide. And these graphene and reduced graphene oxide, they can be derived from the graphite powder itself, and there are various methods by which they can be derived. Various methods have already been reported, and after deriving the graphene from the graphite powder, we can further reduce it to the reduced graphene oxide form also. And there are different methods which have been reported for the reduction also. And in the present work, we have basically fabricated different thin films of the graphene oxide and reduced graphene oxide. And the applications would also be discussed. So basically, the graphene, initially the graphene oxide, this was derived from the graphite powder only using the modified Hammer's method, where the chemical treatment was done to the graphite powder, and initially we are getting the graphene oxide. So this graphene oxide which we are getting here, it is in the brown color solution. And when the further this graphene oxide is being reduced to RGO, or the reduced graphene oxide, the color changes from the solution of the black color, the solution changes. So this can initially be done with the help of various chemical methods. Like for example, here we have reduced it with the help of hydrazine hydrate. But the thing is that when we are reducing it to reduce graphene, RGO, this GO gets reduced to the RGO, it has the property to tend to it starts getting agglomerated. So there is a difficulty in the thin film formation of the RGO. Hence, what we did was later on, the procedure which we followed was that this graphene oxide solution, it was coated onto the glass substrates using the doctor blade technique. After the coating, the thin films of graphene oxide, the films were exposed with the hydrazine hydrate, and then further after the exposure to the hydrazine hydrate, the films were reduced to the RGO. So this brown color film changes to the gray color film, which basically shows the reduction of the graphene oxide films. Further, this graphene oxide film, they have been used. Here we are showing the SEM and the EDEX analysis of the graphene and the reduced graphene oxide, basically which this EDX analysis confirmed the reduction of the graphene from the reduced graphene oxide, and these are the same images which are showing this layered and the crumpled structure of the graphene and reduced graphene oxide. This is the XRD analysis which confirmed the reduction of the graphene oxide to the RGO. If you'll see this broadening of the peak and this disappearance of the peak confirmed that the material has successfully been reduced to the reduced graphene oxide. Further, when the thin films were developed, they have been nowadays, there have a lot of research have been done on the humidity enabled energy power generation. So we have developed these thin films for the humidity driven nano generator only. And here what we have done is initially the coating of the graphene oxide film was coated. Later on, this film was reduced to the RGO. Basically, a bilayer structure has been created using the graphene oxide and reduced graphene oxide. So on the reduced graphene oxide film, another layer of graphene oxide was coated, and then followed by the followed by the metallization of the electrodes. So after when this device was formed, the voltage and the current measurements were taken, and we saw that this device was sensitive to humidity, and a voltage and the corresponding current was generated. So basically, a bilayer device was being fabricated using reduced graphene oxide and graphene oxide. So this is the humidity response of the bilayer device, as we can see over here, within the range of almost 35 to 80% of the humidity. When the humidity was in this range, a corresponding voltage and the current could be observed. So a voltage of approximately 0.9 volt and a current of 0.3 microamperes was generated for the device. And these are the corresponding consecutive repeatability or the cycles for different cycles for which the readings were taken. Repeatability cycles for which the device was studied. Over here, one thing I would like to tell was when the device was being studied and these repeated humidity cycles were taken, graphene, since it has the property of absorbing the water, it is hydrophilic in nature, so it absorbs the water. So when the films were, when the device was studied repeatedly for different consecutive cycles, the material, the film started swelling up, and initially it started peeling off from the substrate. So further, various other studies were also conducted to make the film more stable and for the stability of the device. So another method was adopted, that we fabricated different graphene oxide membranes. So if we go back over here to this procedure, here initially we can say that we fabricated a graphene oxide membrane, reduced it to the RGO membrane, and again coated graphene oxide on those membranes. So we can, basically, if we coming back to this, these results over here, if again the device was studied, so we had better stability and better voltage and the current of the membrane based device as compared to the thin film of the device, of the bilayer device. So other reduction methods for the thin film of the RGO were also studied. These studies were basically carried out to make the device more stable. Other methods like thermal reduction at around 250 degrees Celsius was also done. And then we also electrodeposited reduced graphene oxide on the ITO substrates. So over here we can see this layered structure, which was for the thermal reduction. And these are the nanoparticles were formed when the reduced graphene oxide was electrodeposited on the ITO coated glass substrates. So after when the different coating methods were adopted, we can see from these results that the graphene oxide initially, this was the carbon oxygen ratio for the graphene oxide. For the chemical reduction, if we see, that is from the reduction from the hydrazine hydrate, there was better reduction in the as compared to the other methods for that. And in terms of if we see the sheet resistance and other properties we study, so this reduced graphene oxide from the chemical reduction had better sheet resistance and from as compared from the thermal reduction and the electrodeposition methods. So basically whatever these thin films which we have deposited, we have been using them for different applications. For example, we have used graphene oxide. This graphene oxide is sensitive to humidity. We can use it as the humidity sensor, and we have already, our other studies have also been reported. Because of the time constraint, I couldn't present those work over here right now. And with the chemical reduction, we have fabricated a moisture-driven nanogenerator with the reduced graphene oxide from the thermal reduction and from the electrodeposition. We have used them in the dye-sensitized solar cells and the sensors application. In dye-sensitized solar cells, we are using them as the electrodes. So basically over here, we are using two various different methods. These were studied, and out of these methods for the moisture-driven nanogenerator, it was concluded that all these, out of them, the membrane-based device has better stability and it gave better results in comparison to the thin film device. And the technology which we have used, this moisture-driven power generation, it is useful for the small-scale devices like sensors, wearable electronics also. And by connecting them in series and parallel fashion, we can use it further for the increased voltage and the current. And these other thin films which we have fabricated from other methods, they are useful for sensors, solar cells, and other energy storage devices. So I'm thankful to all the members of the AIARS and our founder, sir, Dr. Ashok Chauhan, for the continuous encouragement and the contribution. Thank you.
Amita, nice presentation. So I would like to, just a moment. Yeah, so you have basically formed the reduced graphene oxide, and you have used the bilayer also because it is reduced from the graphene to reduce to RGO. But my worry is that this interface will not be so smooth for the device kind of thing. So how do you ensure that the interface between the RGO and your graphene is clear? Or means you understand what I'm trying to say?
When we are basically forming the thin film.
Yes, I mean in the form of bilayer when you are forming.
Yes, ma'am.
So how sharp is your interface, and does it bother the device characteristics?
Ma'am, it may, because for example, when we are talking about the thin film, so then it is not hindering the junction which is there. Basically, the mechanism on which we are working is like we need to create the concentration gradient of the H plus ions, because the graphene oxide, it has the functional group. So when it will get interacted with the humidity, and as compared to the reduced graphene oxide, which has less number of oxygen containing groups, so concentration gradient will be created. So based on that principle, we fabricated this device. So as far as thin films are concerned, over there, the bilayer structure, it won't hinder. But yes, in case of the membrane, because membrane has the more thickness, and we have done some thickness studies also. And as the thickness of this graphene layer, which is on the top layer, if the thickness increases, so at a particular thickness, maybe beyond several few microns, so after that, the voltage, yes, it gets affected and the film starts peeling off.
Okay. And one more thing is, why didn't you do Raman measurements on your these films? Because this is the typical characteristics of graphene
Yes,
as
ma'am.
well as
Yes.
But
Ma'am, yes,
I
I am
see
in
it in your presentation.
actually, I got the result for few samples, and for the few right now, they were not available. So that is why they are not presented over here. But yes, we are in the process.
And what was the contact angle you found?
Pardon, ma'am?
What contact angle did you find for your samples? You said that it is hydrophilic in nature, but what is the order of that contact angle?
Ma'am, RGO is hydrophobic in nature.
But you said hydrophilic, I think.
Ma'am,
Okay,
graphene
what was
oxide is
what was the
hydrophilic.
contact angle for both of the cases?
Hello?
Can you tell me the contact angle which you measured?
Ma'am, the contact angle.
Yeah, how do you ensure that it is hydrophobic or hydrophilic in nature?
Ma'am, we did the humidity measurements, and based on that, we concluded that because based on the humidity measurement, initially only the reduced graphene oxide and the graphene oxide, we have done the studies on the with the respect to
That is the
humidity.
sensing
So
part,
the
but
yes, ma'am.
I think you need
Based
to
on
check.
that.
Okay.
Okay, ma'am.
Yeah, okay. Thank you, Amita. Nice
Thank you.
presentation. Yeah. We can move to the last one, and I would like to know the OT number of all of them because she is saying 13, but previous one, Mahima said it was 10. So I'm a little confused. So moderator Akansha is there.
Yes, ma'am.
So can you please help me with these numbers? Mahima was 10.
Ma'am, 9.
She was 9?
Yes, ma'am.
So when I asked her, she said mine is 10.
Oh, no, ma'am, it's 9.
So it is as per the schedule which was provided to us, isn't it?
Yes, ma'am.
She is 13 and the next one is 14.
14.
Okay. Yeah. Okay, so we can proceed with Jyoti Bhattacharya.
Yes. So I would like to invite Ms. Jyoti Bhattacharya, University of Calcutta. Ma'am, please share the screen.
Hello, good afternoon, ma'am.
Yeah, please share your screen. Will you be able to share your screen?
Ma'am, it's visible?
Yes.
Yes, please proceed.
So my topic is International Conference on Semiconductor Technologies, Materials to Chips, Enhancing Efficiency and Stability in Perovskite Solar Cell. 1 minute, ma'am. Yes, ma'am. Sorry. Yeah. So my topic is enhancing efficiency and stability in perovskite solar cell hybrid device architecture. So as we know that perovskite solar cell is a very in thing. So how to efficiently increase the stability, and I have really done work on flexible perovskite solar cells. I have shown this image. So my table of contents includes the introduction, the history of perovskite cell, my novelty of the experiment, the characterization, my result and discussion, and the challenges of using flexible polymer-based solar cells, the evolution of solar photovoltaic technology, perovskite silicon tandem. I have just given a brief about it, my few publication and references and acknowledgement. So the introduction deals with, so this is the main structure of the perovskite solar cell. It has light absorber part, carrier collector part, and the metal contacts. And so this is my history, that perovskite solar cell known for high efficiency and low production cost, and that have garnered attention since 2009, and they have AMX3 stoichiometry, and these two I have generated using this Vesta software, and these are the application of solar cell. They can be, it is a renewable energy form. It can be for remote locations, free, limitless, and environment friendly. So it will also reduce the dependence on fossil fuels. So I have shown one graph of the best research cell efficiencies till now using this multi-junction concentrator, crystalline silicon cell. This is the line, blue line that is showing the crystalline silicon cells, then thin film technologies and emerging PV cells. I have focused on emerging PV organic cells. So this is the solar power fundamentals that include the understanding photovoltaic effect and solar cell technology. And the physics include that N-type has impurities for extra electron. For example, I've given phosphorus, and P-type has one lower electron, for example, boron, and that is the reason we are getting AMX3 structure. And then my novelty is mainly this. We have tried to create the flexible solar cell, and the perovskite material that I have used is barium dot CSSNCl6 over flexible ITO coated PET substrate. So approximately we have got 4.30 power conversion efficiency, and we are trying to achieve more. And the IV characterization I have also shown, and this is a cost effective fabrication process because it has I have only used very low cheap that can be easily manufactured in lab, and the reducing agents all are cheap and it can be easily done. So I have substituted silicon, so that is the most important novelty. And the fabrication of solar cell, first I have taken the PET First, I have taken the PET substrate, and then on that, indium tin oxide, I have coated it. Then I have done the TiO2 paste, titanium oxide. Then the perovskite, I have made perovskite and CuSCN. Perovskite I made separately. Then I have coated it with CuSCN, and then finally with silver paste. So this is the structure, and this is the final result. And I've given the properties that are major point of any solar cell, that is open circuit voltage, short circuit current, maximum power, and the efficiency. And this is the formula, that is eta equal to power by E into A. So under standard condition, this is the standard curve that we are supposed to get, and this is my curve. IV characterization for photovoltaic parameters, I have shown the difference of doped and undoped. So doped, I can see that the efficiency is around 4.3% for 0.82 voltage. This is the short circuit voltage, and the short circuit current 1.60 around, and fill factor is 0.68. I've also shown the PL intensity of, this is the doped one, red one, and the undoped perovskite. So characterization, I have done XRD analysis that has shown the purity and crystallinity of the perovskite, and the Miller indices I have shown. And this is the same, and the EDX analysis same has shown the structural characterization. The grain size we can see clearly. The elemental composition also through EDX I have shown. The carbon, then barium, tin, the percentage weight I have shown. Then I have shown another characterization including atomic force microscopy that has shown the scale around 100 to 300 nanometer, and the individual grain can be clearly visible for the doped perovskite. And also the important plot, that is the UV visible analysis, the top plot. The doped perovskite has shown around 1.85, and the undoped one was 1.95 around. So it has been reduced, so it has achieved the criteria of the doping for perovskite solar cell. And I've also shown the schematic presentation of my full thing, that is the FTO electrolyte to paste it, then the scattering layer, then the iodine dye I've used it in TiO2, and this is ITO coated PET, the base substrate. And I have given another one video of my experiment through LED. Through the artificial light, I have shown that my solar cell has been showing this LED light. This is glowing after I give any source of artificial. And so these are the disadvantages of solar energy. Few I have written, that the initial cost is high. Then the solar panel require a large area to install, and the solution, they can be improved by efficiency and stability of solar cell. So as we increase the efficiency, and also if the stability increases more and more, then we'll be able to replace the fossil fuels. And in short, I have done the evolution of solar photovoltaic technology over the year. Earlier, there was silicon dominance, and now more emerging materials are found. Smart inventors are found, energy storage solution, and digitalization, and on IoT is also coming. AI and IoT can also be done for computational. We can also do I can compare the experimental, and also through computational DFT, we can manufacture the solar cells. And this is the efficiency breakthrough and environmental impact of, I have given few of bifacial technology and tandem photovoltaics, quantum dot solar cell. I'm trying to work on this quantum dot solar cells also. And these are the future prospects. of manufacturing economy. They are helpful in material utilization, economic viability, and the future prospect are also market integration and tandem research cell. So these are the few of the references, my few publications. And I want to acknowledge the head of the department and Dr. Shubhashish Roy for helping me carry out this experiment.
Okay, so Jyoti, nice presentation, and you have touched upon the impact of solar cells, which we are actually large demand of flexible solar cells these days.
Yes. Yes.
So I have like few questions for you. I would like to understand that why your XRD is showing so many peaks. It is showing so much of crystallinity. So are you sure that these sharp peaks are all peaks of your material?
Ma'am, it is showing different phase. I mean, the maximum peak that I have shown is 222. The maximum, the highest Miller indices, that is the best peak for the
Where
10%.
is the FWHM of it? How will you be able to evaluate the FWHM of this peak? These are so much of delta function kind of things.
The temperature is around the whole experiment is done in room temperature only. And
That is more worrisome because it will not lead to so much of crystal phases in the perovskites. So actually this, I think you do it in a smaller scan and slow scan rate so that you will be able to distinguish the peaks. There are certain noise which you need to eliminate.
Okay, ma'am.
Okay, this is
Okay,
just advice, one advice.
yes. You are
And
right.
other thing is this, you have shown that the, what do you have to say about the stability of your samples? Generally, these perovskites, they degrade with time. Do you
So,
have a
ma'am,
comment on about the stability?
ma'am, it is till 5 to 6 days. It is stable. I have shown, and this perovskite, my perovskite soil has shown stability till 6 days.
Till 6 days, okay. And what is
Because
the
I'm
efficiency you
using
obtain?
iodine, so it might degrade after that. 6 days, it is totally stable. So
Okay.
I'm still working on how to increase the stability more.
Yes.
That
So this is not flexible, right? If I believe it, it is on a substrate.
yes, ma'am. ITO coated PET. So that is only flexibility. I mean, this
Okay.
PET substrate PET though is flexible and biodegradable both. So PET substrate is flexible, and I have the figure. I think yes, this is a figure I've tried. I will try to do, and
Yeah.
I
So
think
what is the maximum
this is the
efficiency
figure
you
that I
could
have given. Yes,
obtain?
this is the thing that I have made in lab. So if I bend it, it will be flexible.
But how will you bend it? This is ITO base है ना उसका?
I
This
mean,
your substrate is ITO, right?
yes, ma'am.
If you
I
remove
mean,
it, will
ITO
it be
coated.
able
No.
to
My
hold
substrate is
your holes?
ITO coated PET. My substrate is PET. My substrate is PET, not ITO. It is ITO coated PET, but my substrate is PET. So through the image I'm showing, this can be bendable. So this is ITO coated PET itself. So PET
What is
is
the
bendable.
thickness of
This
this substrate?
yes, ma'am. ITO coated PET is my substrate.
What is the thickness of your substrate, Jyoti?
Thickness. Thickness was 0.35 or some 0.35 nanometer, I think. No, 1000 nanometer, sorry. Yes, ma'am, sorry. 1000 nanometer.
Okay, last question is what efficiency did you obtain for your samples?
Ma'am, 4.53%. Yes, 4.53% efficiency. PC power conversion efficiency was obtained.
Okay, and how many cycles did you repeat to get these kind of, means what is the error in this value?
Error. This error in this value, I mean, yes, it can be increased to more.
Okay, nice.
Once
At least attempt is very good. We need such kind of technology. But one thing is the stability you need to work upon and just characterize a little better. Okay.
my characterization could have been I also think it could be better. Yes, ma'am. I'll try.
Yeah.
Yes.
Nice attempt. Thank you. Thank you, Jyoti. Okay,
Thank you so much.
this finishes our session. So over to the organizers.
Yeah. Thank you, ma'am.